Imagine for a moment that the universe is not silent, but instead a magnificent symphony, a cosmic orchestra where every star, planet, and galaxy contributes its own unique note to an eternal melody. Yet, what if I told you that some of the most profound harmonies in this grand composition have gone completely unheard, hidden within what we once dismissed as mere background noise? There are echoes, whispers from the farthest reaches of space and time that carry secrets capable of reshaping everything we think we know about reality itself. These cosmic echoes aren't just literal sounds reverberating through the void. They are residual energy from the birth of stars, ancient light traveling for billions of years, gravitational ripples from colossal collisions, and even quantum fluctuations that have journeyed across eons to reach us. For decades, many of these signals were overlooked, filtered out as static or anomalies. But what if they actually hold the keys to understanding dark matter, extraterrestrial life, and the very fabric of spacetime? Today, we embark on a journey to uncover 25 forgotten clues buried within these cosmic echoes, each one challenging our deepest assumptions and inviting us to see the universe in an entirely new light. From the mysterious wow signal that might have been a deliberate message from another civilization, to the unexplained motion of interstellar objects like Oumuamua, and the subtle irregularities in the cosmic microwave background that hint at realities beyond our current models, each of these clues represents a piece of a puzzle we are only beginning to assemble. This isn't just about revisiting old data. It's about awakening to the possibility that some of the universe's greatest secrets have been hiding in plain sight all along. So join me as we decode these celestial mysteries, venturing beyond the known to explore a realm where the forgotten becomes foundational, and where every whisper from the cosmos has the power to transform our understanding of existence itself. Think of cosmic echoes not as literal sounds bouncing through space, but as faint, persistent signals, the universe's way of leaving a trail of evidence behind after monumental events. These echoes come in many forms: ancient photons traveling for billions of years, the faint ripples of gravitational waves from colliding black holes, or even subtle quantum imprints from the first moments after the Big Bang. Each one is a message, a piece of data carrying stories from across time and space, often hidden in what we initially mistake for noise or interference. A perfect example is the cosmic microwave background radiation. When it was first detected in the 1960s, it appeared as little more than a uniform haze of microwave static, the faint afterglow of the Big Bang. But upon closer inspection, scientists discovered tiny variations in temperature, tiny wrinkles in the fabric of spacetime that revealed the seeds of all cosmic structure, galaxies, clusters, and the vast web of matter we see today. What was once considered background noise became one of the most important clues to understanding the origin of the universe. This pattern of discovery repeats itself throughout the history of astronomy. Time and again, phenomena initially dismissed as instrumental error or cosmic static have turned out to hold revolutionary insights. These echoes are like breadcrumbs scattered across the cosmos, left behind by supernova explosions, galactic collisions, or even unknown physical processes. They linger just at the edge of perception, waiting for the right technology or the right perspective to be understood. And that's exactly what makes them so compelling. Many of these signals are not just faint, they're anomalous. They don't fit neatly into our existing models. They challenge what we think we know, whether it's an unexpected frequency drift in a radio signal, a slight mismatch in the motion of a spacecraft, or an unusual distribution of energy in gamma-ray data. These irregularities are often the starting point for entirely new fields of inquiry. By learning to listen more carefully, by refining our instruments and questioning our assumptions, we open the door to discoveries that can fundamentally alter our understanding of reality. The echoes are there, all around us, carrying information from some of the most dramatic and distant events in the cosmos. They remind us that the universe is still speaking, if only we're willing to pay attention to what we've previously overlooked. Now consider the WOW signal, a burst of radio energy so powerful and unusual that the astronomer who discovered it circled the printout and wrote, "Wow." Right next to the data, detected in August 1977 by the Big Ear radio telescope at Ohio State University. This signal lasted for 72 seconds and came from the direction of the constellation Sagittarius. It was 30 times stronger than the background noise and matched almost perfectly the expected signature of an interstellar transmission. But then, just as suddenly as it appeared, it vanished. Follow-up observations weeks, months, and even years later heard nothing but silence from that same patch of sky. For decades, the prevailing explanation has leaned toward a natural, if unknown, astrophysical event or perhaps a one-time glitch. But what if we've been asking the wrong questions? Instead of wondering why we never heard it again, we should be asking what we might have missed the first time. A deeper look at the signal's characteristics reveals subtle complexities that are often glossed over. Its intensity rose and fell in a gradual curve over the 72-second window, exactly as you would expect from a stationary source passing through the telescope's fixed field of view. This isn't the jagged, chaotic profile of random noise. It's a clean, predictable pattern. Even more intriguing is the signal's narrowband nature. It was concentrated on one specific frequency, around 1420 MHz, which is significant because that frequency happens to be close to the hydrogen line, a part of the radio spectrum that many scientists have long speculated would be a logical choice for interstellar communication. Hydrogen is the most common element in the universe, so a signal near that frequency could be a kind of universal hello. But here's where it gets really interesting. The WOW signal also exhibited a slight frequency drift. This tiny shift could be explained by the Doppler effect, perhaps caused by the motion of the source relative to Earth. While a natural celestial object could produce drift, the specific, smooth nature of this shift has led some researchers to propose it might carry encoded information, a form of modulation that could be artificial. Researchers like Robert Gray have spent years reanalyzing the data, arguing that the signal's properties are consistent with what we might expect from a deliberate broadcast. The fact that it hasn't repeated might not mean it was a fluke. It could mean it was never intended to be continuous. Imagine a civilization sending out targeted, intermittent probes or beacons instead of a constant, energy-intensive signal. Or consider the possibility that the signal was meant for someone else, and we simply happened to be in the way for one brief moment. Our own human broadcasts into space, like the Arecibo message, were sent as single, powerful bursts, not endless loops. If another intelligence did the same, we might only get one chance to hear it. This shifts the entire way we should think about the search for extraterrestrial intelligence. We often assume an alien signal would be persistent, obvious, and easily verifiable. But the WOW signal challenges that assumption. It suggests that cosmic messages might be fleeting, subtle, and easily mistaken for background noise if we're not listening in exactly the right way at the right time. It urges us to go back through old datasets with new, more sophisticated algorithms, looking not just for loud, repeating signals, but for faint, structured patterns hidden in what we once dismissed as interference. The greatest hello in history might have already happened, and we might have almost missed it, while the WOW signal invites us to reconsider what we might be missing in the depths of space. another set of clues was being recorded much closer to home, emanating not from distant stars, but from humanity's own robotic ambassadors as they journeyed toward the edge of our solar system. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were pioneers in every sense of the word. They were the first to travel through the asteroid belt, the first to visit Jupiter and Saturn, and the first human-made objects set on a trajectory to leave the solar system entirely. But as they sailed farther and farther from the Sun, something peculiar began to happen. Engineers tracking the probes noticed an almost imperceptible anomaly, a tiny, unexplained deceleration acting on both spacecraft, as if some faint, unseen force were gently tugging them back toward the inner solar system. This deviation was incredibly small, amounting to less than a billionth of the acceleration we feel due to Earth's gravity, but it was persistent, consistent, and undeniably present in the data. For years, this pioneer anomaly captivated physicists and astronomers, sparking debates and theories that ranged from the mundane to the revolutionary. The most widely accepted explanation, eventually put forward by NASA's own team, attributed the deceleration to thermal radiation. The idea was that heat radiating unevenly from the spacecraft's nuclear power sources and instruments could create a faint but measurable push in the opposite direction, a kind of photon recoil effect. It was an elegant solution, and for many it closed the case. But what often goes unmentioned is that even after accounting for thermal effects, some subtle discrepancies in the acceleration data remained. These residual anomalies were small enough to dismiss as margin of error, yet they persisted across both missions, suggesting that perhaps the full story hadn't been told. This is where the clue truly lies, not in the anomaly itself, but in the data that didn't quite fit the official explanation. Some researchers have proposed that these tiny deviations could be echoes of something far more profound. Interactions with dark matter, for instance, or evidence of modified gravity laws that differ from Einstein's general relativity on very large scales. Imagine if the spacecraft were passing through diffuse clouds of dark matter concentrated in the outer solar system, experiencing just enough gravitational drag to slow their progress. Or consider the possibility that our understanding of gravity itself is incomplete, that on interplanetary scales, gravity behaves in ways we haven't yet accounted for. There are even more speculative ideas, such as the influence of extraspatial dimensions or unknown long-range forces. While these concepts might sound like science fiction, they emerge naturally from attempts to reconcile fundamental physics with observational data. The key point is that the Pioneer anomaly, or more precisely, the unresolved nuances within it, represents a classic example of how science often operates. We tend to accept the simplest explanation that fits most of the data, but in doing so, we sometimes risk overlooking the faint signals that could lead to deeper truths. What's especially compelling about this clue is that it emerged from technology that was, by today's standards, relatively primitive. The Pioneer probes were designed and built decades ago with limited instrumentation and communication capabilities. Yet they managed to record data that we are still interpreting and reinterpreting today. This highlights an important lesson. Sometimes, the tools we already have can reveal new mysteries if we're willing to look at the data with fresh eyes and an open mind. Revisiting the Pioneer data with modern analytical techniques and improved modeling could help us determine whether those residual anomalies were merely noise or something more significant. New missions equipped with more precise navigation and measurement systems might be designed to test these possibilities directly. In a way, the Pioneer anomaly serves as a reminder that some of the most intriguing clues in science aren't always found in dramatic, headline-grabbing discoveries. they can be hidden in the quiet, overlooked details of decades-old data, waiting for someone to notice. Then came Oumuamua, a name that means scout or messenger from afar in Hawaiian, and it truly lived up to that title. In October 2017, astronomers spotted this strange object hurtling through our solar system, and it was immediately clear that this was no ordinary asteroid or comet. Its trajectory was hyperbolic, meaning it wasn't bound by the sun's gravity. It was just passing through, the first confirmed visitor from another star system. But as scientists tracked its path, they noticed something that defied simple explanation. Oumuamua was accelerating away from the sun in a way that gravity alone couldn't account for. This non-gravitational acceleration sent ripples through the astronomical community. For comets, such acceleration is usually caused by outgassing. The sun's heat vaporizes ice on the surface, creating jets of gas that act like natural thrusters. But here was the problem. Oumuamua showed no visible signs of outgassing. No coma, no tail, no dusty envelope that telescopes could detect. This absence led to a wave of speculation, including the provocative suggestion that Oumuamua might be an artificial object, perhaps a light sail or a probe from another civilization. While that idea captured headlines, it also overshadowed more nuanced and perhaps more profound possibilities hidden in the data. Look closer, and you'll find that Oumuamua's motion held additional clues. Its acceleration wasn't smooth. The object was tumbling, rotating chaotically every 7 or 8 hours. This tumbling motion is unusual for a body being pushed by outgassing, which typically leads to more stable rotation. Then there were its spectral properties or lack thereof. When astronomers tried to analyze its composition using spectroscopy, they found it unusually dark and red, reflecting very little light and offering no clear spectral fingerprints that would reveal what it was made of. These details, often glossed over in broader discussions, point toward something stranger than a simple comet or asteroid. One compelling theory suggests that Oumuamua could be a fragment from a disrupted exoplanet, a piece of a rocky world torn apart by gravitational forces around its parent star. In such a scenario, the object might have a fractured, porous structure, almost like a cosmic pumice stone. When heated by the sun, trapped gases deep within its pores could be released, producing enough thrust to explain the acceleration without generating the visible dust clouds typical of comets. This would make Oumuamua not just a weird rock, but a relic from another planetary system, a physical echo of processes that shaped worlds far beyond our own. Another possibility is that Oumuamua is composed of molecular hydrogen ice, a substance that would vaporize under the sun's heat without leaving dusty traces. Or perhaps it's a chunk of nitrogen ice, similar to what we see on the surface of Pluto. These exotic compositions are rarely observed in our solar system, but they might be common elsewhere. What's fascinating is that each of these explanations challenges our existing categories. We're used to thinking of celestial bodies as either rocky asteroids or icy comets, but Oumuamua seems to defy that binary classification. It forces us to expand our definitions and consider that the universe might be far more diverse than we've assumed. Beyond its physical nature, Oumuamua's journey tells a broader story. Its presence suggests that interstellar space is filled with such objects, countless travelers drifting between stars, each carrying clues about the formation and evolution of planetary systems. In fact, subsequent discoveries like the interstellar comet Borisov support this idea, but Oumuamua remains unique because of its ambiguity. It passed by too quickly for detailed observation, and by the time we realized how extraordinary it was already too far away to study further. This underscores a critical lesson. Sometimes the most important clues are fleeting, and we must be prepared to recognize and investigate them quickly. What's perhaps most revealing about Oumuamua is not just what it was, but how we reacted to it. The initial leap toward artificial origins reflects a deep-seated tendency to categorize the unfamiliar as either mundane or miraculous, to assume that anything we don't immediately understand must either be nothing special or something extraordinary. But the truth often lies in the middle, in the subtle details that require patience and creativity to unravel. Oumuamua's acceleration, its tumbling motion, its spectral silence, these aren't just anomalies, they're invitations to rethink what's possible. They remind us that the cosmos is full of objects and phenomena that don't fit neatly into our textbooks, and that every unexplained detail could be a doorway to a new understanding of the universe. Now let's shift our gaze from solitary interstellar travelers to one of cosmology's most enduring puzzles, the case of the missing Baryons. According to our most precise calculations of Big Bang nucleosynthesis, the early universe should have created a specific amount of ordinary matter, what physicists call baryonic matter. This includes all the atoms and particles that make up stars, planets, and even ourselves. Yet when astronomers began inventorying the present-day universe, they came up short. Nearly half of this expected matter seemed to have vanished without a trace. For decades, this discrepancy presented a fundamental problem. Where could all that material have gone? We could account for the matter in galaxies and clusters, but that only represented about half of what should be there. Some scientists even wondered if our understanding of the Big Bang itself might be flawed. But the truth, as we're now discovering, is that the matter was never truly missing. We simply hadn't been looking in the right way or with the right tools. The solution appears to lie in what astronomers call the warm-hot intergalactic medium, often abbreviated as WIM. Picture this: vast filaments of extremely diffuse gas stretching between galaxies and galaxy clusters, forming a cosmic web that permeates the entire universe. This gas isn't cold and dark, it's heated to temperatures between 100,000 and 10 million degrees Kelvin, causing it to emit faint signals in the X-ray and ultraviolet parts of the spectrum. These signals are so subtle that for years they blended into the background, indistinguishable from noise with the instruments we had available. What's fascinating is how researchers finally began detecting this elusive component. They used a technique similar to how you might detect fog by looking at how it dims distant lights. Astronomers observed the light from extremely bright quasars, distant galactic nuclei, as it passed through these intergalactic regions. By analyzing how specific wavelengths of light were absorbed, they could infer the presence and properties of the gas these rays had traveled through. The signatures were incredibly faint, like trying to hear a whisper across a crowded stadium, but with sensitive enough equipment, the pattern began to emerge. New space telescopes like the European Space Agency's Newton and NASA's Chandra X-ray Observatory have been crucial in this detection effort. Their improved resolution and sensitivity allow them to pick up the subtle X-ray emissions from these vast cosmic structures. Similarly, ultraviolet telescopes like the Hubble Space Telescope have detected absorption lines that reveal the presence of highly ionized oxygen and other elements within these filaments, providing further evidence for this hidden reservoir of matter. The implications of this discovery are profound. First, it means that our inventory of the universe's ordinary matter is now much more complete. We've found where that missing component has been hiding. Second, it reveals that the cosmic web isn't just a theoretical concept. It's a physical structure made of real material that plays a crucial role in how galaxies form and evolve. Gas from these filaments continually feeds into galaxies, providing the raw material for new stars, while also serving as a repository for material ejected from galaxies through supernova explosions and other processes. This clue also serves as a powerful reminder of how technological limitations can shape our understanding of the cosmos. For years, the WIM was essentially invisible to us, not because it wasn't there, but because we lacked the tools to see it. This pattern repeats throughout the history of astronomy, from Galileo's first telescope revealing mountains on the moon to radio telescopes unveiling the cosmic microwave background. Each technological advance doesn't just give us better data, it fundamentally changes what we can know about the universe. Perhaps most exciting is what this suggests about other cosmic mysteries. If half the ordinary matter in the universe was hiding in plain sight for decades, what else might we be missing? The same principle could apply to our search for dark matter or dark energy substances that currently elude direct detection but whose influence we clearly see. Maybe we simply need to develop new ways of looking, or consider that these mysterious components might be manifesting in ways we haven't thought to investigate. The story of the missing Baryons ultimately teaches us a lesson about scientific humility and persistence. It shows that even when our models and observations don't align, the universe usually has an explanation. We just need to keep searching with open minds and increasingly sophisticated tools. What was once a troubling discrepancy in our cosmic accounting has become one of the most important clues to understanding the large-scale structure of our universe, reminding us that sometimes the answers are right there in front of us, waiting for our vision to improve enough to see them. Now consider fast radio bursts, some of the most energetic and enigmatic signals ever detected in the universe. Imagine a pulse of radio waves that travels across billions of light years, carrying in mere milliseconds more energy than our sun emits in days. When these events were first discovered in 2007, astronomers assumed they were catastrophic, one-off explosions, like the final scream of a collapsing star or the merger of two neutron stars. But then, in 2016, everything changed. That's when astronomers realized that one source, known as FRB 121102, wasn't just a single event. It was repeating. This wasn't just a minor detail, it was a revolution in our understanding. Suddenly, these incredibly powerful signals couldn't simply be explained by singular cataclysms. Whatever was producing them had to survive the event itself, meaning the source had to be something capable of generating multiple enormous outbursts over time. The immediate and most plausible explanation pointed to magnetars, a type of neutron star with an immensely powerful magnetic field. These cosmic powerhouses can experience starquakes or magnetic eruptions that might release enormous energy in short, intense bursts. But while that may account for some of these signals, the repeating bursts from FRB 121102 and others like it show features that are difficult to explain with even the most extreme astrophysical models. Look closer at the data, and you'll find that these repeating bursts are not just random. They exhibit intricate patterns, subtle frequency drifts, where the signal changes pitch during the burst, and complex sub-pulse structures that hint at an organized emission process. Some bursts even show nearly 100% polarization, meaning their radio waves are aligned in a specific direction, which can occur when signals pass through strong magnetic fields. But here's where it gets truly fascinating. Some of these properties look less like natural astrophysical phenomena and more like what we might expect from an engineered signal. This isn't to say that fast radio bursts are definitely evidence of extraterrestrial technology, but it does mean we can't dismiss the possibility outright. Imagine, for a moment, a civilization capable of harnessing the energy of an entire star to power a transmitter aimed across the cosmos. Such a device might produce exactly the kind of intense, directed bursts we observe. The repetition could be intentional, a beacon designed to catch the attention of anyone listening. The frequency drifts and sub-pulse structures might even encode information, much like how we use modulation in human communication systems to carry data. Even if the explanation turns out to be purely natural, these signals are far from understood. The repeating patterns suggest that the environment around the source is incredibly dynamic and structured. For example, some models propose that these bursts might be produced by a highly magnetized neutron star orbiting a black hole, with interactions between the two objects creating periodic opportunities for energy release. Others suggest that the repeating patterns could be due to precession, a wobble in the rotation of a magnetar that periodically directs beams of radiation toward Earth. What's remarkable is how much we can learn from even the smallest details of these signals. The way the radio waves are dispersed, spread out across frequencies, tells us about the material they've passed through on their journey across the universe. This allows astronomers to map the distribution of ionized gas between galaxies, essentially using fast radio bursts as tools to probe the cosmic web. Polarization gives clues about the magnetic fields they've traveled through, helping us understand the structure of space on the largest scales. Yet for all we're learning, the finer details of many bursts remain unanalyzed. Early detections were often treated as isolated curiosities, and it's only recently that we've begun systematic studies of their properties. New telescopes, like the Canadian Hydrogen Intensity Mapping Experiment, are now discovering these events by the dozens, providing a wealth of data that earlier astronomers could only dream of. Machine learning algorithms are being deployed to sift through this data, looking for patterns that human eyes might miss. This clue, the repeating patterns in fast radio bursts, challenges us to think differently about how we categorize cosmic signals. For years, the assumption was that anything this powerful and short-lived had to be a destructive event. But the repeaters show that the universe is capable of producing such signals in a persistent, structured way. They remind us that nature is often more creative than our theories, and that what we might initially dismiss as noise could actually be a message, whether from a magnetar's magnetic field or something even more extraordinary. The echoes are there, waiting in the data for us to finally understand what they're trying to say. But just as fast radio bursts challenge our assumptions about cosmic signals, another mystery lies hidden in the oldest light we can observe, light that has traveled for over 13 billion years to reach us. The cosmic microwave background, that faint afterglow of the Big Bang, is often described as the universe's baby picture. According to our most fundamental cosmological principles, this radiation should be almost perfectly uniform in every direction, a nearly isotropic sea of microwaves that confirms the universe is broadly the same no matter where you look. But when scientists began mapping it with incredible precision using satellites like WMAP and Planck, they found something deeply puzzling. The universe seems to have a preferred direction, an alignment so unexpected that astronomers half-jokingly named it the axis of evil. This isn't about good or evil in any moral sense, of course. The name reflects how troubling this discovery is to our standard models of cosmology. The axis of evil refers to a strange large-scale alignment in the temperature fluctuations of the cosmic microwave background. These tiny variations, hot and cold spots that represent the seeds of future galaxies, should be randomly distributed with no particular orientation or pattern. Instead, researchers found that some of the largest fluctuations appear to be aligned along a specific axis, almost as if the entire early universe was subtly structured around a preferred direction. This isn't just a minor statistical fluke. It's a fundamental challenge to the cosmological principle, which states that the universe should be homogeneous and isotropic on large scales. If there's a preferred direction woven into the fabric of the cosmos itself, then one of the foundational pillars of modern cosmology might need rethinking. Initially, many scientists dismissed these alignments as instrumental noise or systematic errors in the data processing. After all, measuring minute temperature differences in microwave radiation from the edge of the observable universe is an incredibly difficult task, fraught with potential sources of contamination. But as more data came in from subsequent missions, and as independent teams analyzed the results, the signal persisted. The axis of evil refused to go away. This forced the scientific community to consider more radical explanations, ideas that venture into realms we're only beginning to explore. One possibility is that these alignments are echoes from a time before the Big Bang. Inflation theory, which describes the universe's rapid expansion in its first fractions of a second, generally predicts a random distribution of fluctuations. But if something existed before inflation, some pre-existing structure or field, it could have imprinted a directionality on the newborn universe. Think of it like a piece of fabric that was stretched during inflation. If the fabric had a weave or pattern before stretching, that pattern might still be faintly visible even after being expanded to cosmic scales. This could mean our universe inherited its large-scale structure from a previous cosmic epoch, something that existed before time as we know it began. Another explanation involves unknown physics during the inflationary period itself. Perhaps the laws of physics aren't completely symmetric in all directions, leading to subtle preferences in how structures formed. Or maybe dark energy or dark matter interact in ways that create large-scale anisotropies we haven't yet accounted for in our models. Some theorists have even proposed that the axis of evil could be evidence of our universe colliding with another universe in the multiverse, a cosmic bruise left by contact with a separate reality. What makes this clue so compelling is that it's not just about one anomaly. It's about how we approach anomalies in general. For years, the axis of evil was largely pushed to the sidelines of cosmological research because it didn't fit neatly into existing theories. But with advances in technology and data analysis, we're now in a position to investigate it more seriously. Machine learning algorithms can scour the cosmic microwave background data for subtle patterns that human eyes might miss. Cross-correlating this data with other observations like the distribution of galaxies or the polarization of the CMB might reveal whether this alignment is real and what it might be connected to. The European Space Agency's Planck satellite provided our most detailed map of the cosmic microwave background yet, and while it confirmed many aspects of the standard cosmological model, it also left the mystery of the axis of evil largely intact. Future missions like the proposed CMB-S4 project aim to measure the polarization of the CMB with unprecedented precision, potentially offering new clues about this large-scale alignment. These observations could help distinguish between different explanations, perhaps revealing whether we're seeing evidence of pre-Big Bang physics, modified gravity, or something even more extraordinary. This clue reminds us that even our most successful scientific theories are provisional. They're the best explanations we have until new data comes along that forces us to revise them. The cosmological principle has been incredibly productive, helping us understand the large-scale structure of the universe and guiding the development of models like the Big Bang theory. But if the axis of evil turns out to be real and significant, it could open the door to a new cosmological revolution, showing that the universe isn't as uniform as we thought, and that its history might be far richer and more complex than we ever imagined. Deep within the heart of our own galaxy, a silent, invisible storm has been raging, a tempest of unimaginably high-energy light that, for years, we simply subtracted from our data as mere background noise. This is the galactic center gamma ray excess, a mysterious overabundance of gamma rays detected by the Fermi Gamma Ray Space Telescope emanating from the region around the Milky Way's core. On the surface, the center of our galaxy is a chaotic and violent place, teeming with known gamma ray sources, spinning pulsars, the remnants of supernova explosions, and the intense environment around the supermassive black hole Sagittarius A star. When astronomers built models to understand this chaos, they accounted for all these known contributors, expecting the remaining signal to be quiet, but it wasn't. A persistent, glowing excess of gamma rays remained, and its characteristics point to something entirely new and unexplained. The initial and most tantalizing hypothesis was that this glow is the long-sought signature of dark matter. The theory is elegant. Dark matter particles, which outweigh normal matter 5 to 1 in the universe, could be accumulating in the dense gravitational well at the galaxy's center. There, they might occasionally collide and annihilate each other, converting their mass directly into energy and producing a smooth, symmetrical fountain of gamma rays. The energy spectrum of the excess, the specific color of these gamma rays, even matches what some models predict for the annihilation of certain proposed dark matter particles called WIMP, or weakly interacting massive particles. It was a potential breakthrough, a way to finally see the invisible stuff that holds galaxies together. But as researchers looked closer, complications emerged. The spatial distribution of this gamma-ray glow isn't quite perfect. While it is broadly spherical and centered on the galactic core, as a dark matter signal should be, some analyses suggest it might be slightly more elongated or lumpy than the clean, smooth halo predicted by the simplest models. This has led to a competing explanation: a vast, unseen population of millisecond pulsars. These are ancient, incredibly dense neutron stars that spin hundreds of times per second, sweeping the cosmos with powerful beams of radiation that include gamma rays. Thousands of such faint, point-like sources could blend together into a smooth, excess glow that mimics a dark matter signal. Yet, this explanation has its own problems. Observations with powerful radio telescopes have failed to detect the number of pulsars that would be required to produce such a bright and widespread signal. Furthermore, the energy spectrum of the excess, while close, doesn't match the combined output of known pulsar populations perfectly. We're left in a fascinating stalemate where the two leading explanations both fit parts of the data beautifully, but neither provides a complete picture. This impasse is where the real clue is buried, not in confirming one theory, but in the failure of both to fully explain what we're seeing. This forces us to consider even more exotic possibilities. Could the signal be coming from a population of primordial black holes? These hypothetical black holes, theorized to have formed in the intense density of the early universe, could be swarming the galactic center. As they feed on gas and dust, their violent accretion processes could generate the observed gamma rays. Or perhaps we're seeing the signature of something entirely unforeseen, like decays of exotic particles or even evidence of new fundamental forces at work. The very ambiguity of the signal is its most profound feature. It is a clear message from the universe that our current catalogue of cosmic phenomena is incomplete. What's truly remarkable about this clue is how it was discovered. It wasn't found by looking directly at a bright object, but by meticulously sifting through years of data and carefully subtracting everything we thought we understood. The signal revealed itself in the residuals, the leftover data points that didn't fit the model. In many scientific analyses, these residuals are often dismissed as statistical noise or systematic error, the meaningless scatter around a perfect fit. But here, the residual was the signal. It's a powerful lesson in scientific humility. Sometimes, the universe's most important messages are not shouted from the rooftops, but whispered in the data we were prepared to throw away. This gamma-ray excess is a ghost in the machine of our galaxy, a persistent echo from the darkness that refuses to be ignored and challenges us to expand our understanding of physics itself. While the mysteries of the galactic center involve forces operating on unimaginably large scales, some of the solar system's most intriguing puzzles are waiting just beyond the planets we know, in a region of icy debris that marks the edge of our familiar cosmic neighborhood. The Kuiper Belt, that vast donut-shaped ring of frozen worlds beyond Neptune, is not the smoothly fading collection of objects we once expected it to be. Instead, it holds a stark and sudden boundary, a dramatic drop in the number of objects at a distance of about 50 astronomical units from the Sun. Astronomers call this feature the Kuiper Cliff, and its existence challenges everything we think we know about how the solar system formed and what might still be lurking in its dark outer reaches. Standard models of planetary formation suggest that the Kuiper Belt should gradually thin out the farther you go from the Sun. The early solar system was a swirling disk of gas and dust, and as planets coalesced, they swept up material in their vicinity, but their gravitational influence weakens with distance. Out beyond Neptune, we should see a relatively smooth distribution of icy bodies, leftover building blocks from the solar system's infancy that never came together to form a planet. But the data from telescopes tells a different story. At around 50 astronomical units, that's 50 times the distance from Earth to the Sun, the number of detectable objects doesn't just gradually decline, it plummets. It's as if someone built a wall out in the darkness, a definitive edge to the reservoir of ancient material. This sharp boundary is a clear sign that something significant happened out there, an event or presence that swept the region clean or prevented objects from accumulating beyond that point. The most captivating explanation, and the one that has captured public imagination, is the possibility of an unseen planet, a so-called Planet 9. This would not be a small world, but a substantial planet, perhaps several times the mass of Earth, orbiting the Sun on a distant, elongated path. Its gravitational influence could be acting like a shepherd, clearing out a zone of the Kuiper Belt by either ejecting objects from the solar system entirely, sending them plunging inward toward the Sun, or shepherding them into orbits that keep them clustered away from the cliff edge. The gravitational pull of such a planet would create precisely the kind of abrupt termination we observe. However, Planet 9 is not the only potential architect of this cosmic boundary. Another compelling theory points to a dramatic event in our solar system's youth, a close encounter with another star. In the Sun's early days, it was born in a cluster with thousands of other stars, all orbiting relatively closely together before gradually drifting apart. During this chaotic period, a passing star could have swung through the outer solar system, its gravity violently stripping away the outer layers of the Kuiper Belt and leaving behind the sharp edge we see today. This stellar flyby would have been a fleeting event on a cosmic timescale, but its echo would be permanently frozen into the architecture of our solar system, a lasting scar from a violent childhood encounter. There are even more exotic possibilities. Some researchers have proposed that the Kuiper Cliff could mark the transition where the Sun's primordial disk of material simply ended, perhaps because the cloud from which our solar system formed had a finite size or because of interactions with the ambient interstellar medium of the time. While this is a simpler explanation, it struggles to account for the sharpness of the drop-off, which seems to demand a more dynamic and forceful cause. What makes the Kuiper Cliff such a powerful clue is that it's not just a theoretical problem, it's an observational one. Every object we detect near this boundary becomes a crucial data point. By studying the orbits, compositions, and even the colors of these distant icy bodies, we can look for patterns that might reveal the nature of the force that shaped them. For instance, if Planet 9 is real, its gravity should have shepherded a population of objects into orbits that are tilted and clustered in a specific way. Astronomers are actively searching for these patterns, and each new discovery of a distant Kuiper belt object adds another piece to the puzzle. This search is technologically demanding. These objects are incredibly faint, reflecting only tiny amounts of sunlight, and they move very slowly against the background stars. It requires the most powerful telescopes and painstaking survey work to find them. Yet, with every new observatory that comes online, like the Vera C. Rubin Observatory, our ability to probe this dark frontier improves dramatically. We are on the verge of mapping the outer solar system with a precision that was unimaginable just a decade ago. The Kuiper Cliff stands as a testament to the fact that even our own cosmic backyard still holds profound secrets. It reminds us that the solar system is not a static museum display but a dynamic system with a rich and violent history. The forces that sculpted its outer edges may still be at work today, and by deciphering this forgotten clue, we aren't just learning about a distant population of icy rocks. We are uncovering the story of how our planetary family was built and what unseen actors might still be playing a role in its evolution. While we often look to the vast structures of the cosmos for answers, some of the most startling clues arrive not as gentle whispers from the void, but as unimaginably powerful bullets fired from the depths of space. These are ultra-high-energy cosmic rays, subatomic particles accelerated to energies that defy belief, carrying with them the echoes of the most violent events in the universe. The most famous of these, detected in 1991 over Dugway Proving Ground in Utah, was so astoundingly powerful that it earned the nickname the "Oh my God" particle. This single proton was traveling at a velocity so close to the speed of light that it possessed the kinetic energy of a well-thrown baseball, all compressed into a single fundamental particle. The existence of such particles presents a profound cosmic puzzle. According to our current understanding of physics, there are simply no known objects in our galaxy powerful enough to accelerate a proton to such an extreme energy. Even the most powerful natural accelerators we know of, like the expanding shock waves of supernova remnants, fall orders of magnitude short of the force required. This forces astronomers to look far beyond the Milky Way to the most energetic engines in the universe. The prime suspects are active galactic nuclei, the superheated, ultra-bright regions surrounding supermassive black holes as they devour matter. The intense magnetic fields and relativistic jets produced by these monsters could, in theory, act as a cosmic particle accelerator of unimaginable scale. Other potential sources include gamma-ray bursts, the cataclysmic explosions marking the death of massive stars or the merger of neutron stars, which can briefly outshine entire galaxies. But here's where the mystery deepens into a genuine clue. If these particles are indeed coming from such distant, extragalactic sources, they should not be able to reach us at all. The universe is filled with the faint glow of cosmic microwave background radiation, the leftover heat from the Big Bang. For a proton traveling at nearly the speed of light, this radiation is blue-shifted into a barrage of high-energy gamma rays. Colliding with these gamma rays would cause the ultra-high-energy proton to lose a significant amount of its energy long before it could ever reach Earth. It's a cosmic speed limit that these particles seem to break, suggesting either that they are coming from much closer sources within our galaxy, which we haven't identified, or that our understanding of particle physics itself is incomplete under such extreme conditions. The path these particles take is another layer of the enigma. Cosmic rays are charged particles, which means their trajectories are bent and scrambled by the magnetic fields that permeate interstellar and intergalactic space. By the time one reaches our detectors, Pinpointing its origin is like trying to trace a single raindrop back to a specific cloud during a hurricane. We know the general direction it came from, but the exact source is lost in a fog of magnetic deflection. This is why the detailed composition of these particles is so crucial. If we can analyze not just their energy, but also their type, whether they are protons, heavier atomic nuclei, or even something more exotic, we can start to reverse engineer their journey. Heavier nuclei will be deflected less by magnetic fields, offering a slightly clearer, though still fuzzy, pointer back to their source. This is where the forgotten clue lies. For decades, the primary focus has been on detecting these rare events and measuring their immense energy. The finer details of their atomic makeup and their precise arrival directions have often been secondary considerations, buried in the overwhelming shock of their detection. But by revisiting this archival data with modern statistical techniques and cross-referencing it with new multi-messenger observations, like matching a cosmic ray detection with a neutrino or gravitational wave event from the same patch of sky, we could uncover patterns we've never seen before. Perhaps these anomalous particles are not just astronomical curiosities, but messengers of new physics. Some theorists propose they could be the signature of decaying super-heavy dark matter particles. If such a particle, left over from the early universe, were to decay somewhere in the halo of our galaxy, it could produce a shower of ultra-high-energy standard particles, including protons, that wouldn't have to travel far enough to be slowed down by the cosmic microwave background. This would neatly solve the problem of their arrival and point directly to the invisible dark matter that shapes the cosmos. Alternatively, they might be evidence of topological defects in the fabric of spacetime itself, or relics from a more violent epoch of the universe. The ongoing hunt for these particles continues with sophisticated observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, which use vast networks of detectors to capture the extensive air showers these rays create when they strike the atmosphere. Each detection is a piece of a puzzle, a cosmic echo from a violent event that may have occurred billions of years ago and billions of light years away. They remind us that the universe is capable of energies we are only beginning to comprehend, and that the most fundamental particles can carry the secrets of the most colossal phenomena. By listening carefully to these high-energy messengers, we might finally hear the faint whisper of dark matter's decay or the distant roar of a physical law we have yet to discover. Now consider one of the most pressing and persistent puzzles in modern cosmology, a discrepancy so fundamental that it threatens to unravel our entire understanding of the universe's expansion. For decades, astronomers have worked to measure the Hubble constant, the rate at which the universe is expanding today. It seems like it should be a straightforward number to pin down, but instead, it has become the center of a growing controversy known as the Hubble tension. Here's the problem. When we measure the expansion rate using the early universe specifically by studying the cosmic microwave background, the afterglow of the Big Bang, we get one value. But when we measure it using modern local observations, like the distances to supernova in nearby galaxies, we get a significantly different, faster rate. These two methods, both rigorously tested and independently verified, disagree by about 10%. That might not sound like much, but in the precise world of cosmology, it's a glaring inconsistency that suggests something profound is missing from our models. This isn't just a minor accounting error, it's a direct challenge to the standard model of cosmology, often called the lambda-CDM model, which describes a universe dominated by dark energy and cold dark matter. This model has been incredibly successful at explaining a vast array of observations, from the large-scale structure of galaxies to the abundance of light elements. But the Hubble tension is a crack in its foundation. If our understanding of the universe's composition and evolution were complete, these two completely different ways of measuring its expansion should converge on the same number. The fact that they don't means that the model might be incomplete. We're not just dealing with a measurement error, we're likely staring at a clue pointing toward new physics. One of the most compelling ideas proposed to resolve this tension is the concept of early dark energy. In the Standard Model, dark energy is the mysterious force causing the universe's expansion to accelerate, but it's thought to have become dominant only in the last several billion years. Early dark energy suggests that a similar form of energy was also active in the universe's first few 100,000 years. This transient burst of extra energy would have subtly altered the physics of the early universe, changing how sound waves propagated in the primordial plasma, and thereby affecting the patterns we see in the cosmic microwave background. This would mean that when we use the CMB to calculate the Hubble constant, we've been basing our math on an incomplete picture of the early universe. Correcting for this early dark energy could bring the early universe measurement into alignment with the faster rate we see today. It's an elegant solution, suggesting that dark energy isn't a late-life feature of the cosmos, but has been popping in and out of existence all along. Another radical possibility is that our theory of gravity itself, Einstein's general relativity, needs to be modified on the largest scales. For a century, general relativity has passed every test thrown at it, from predicting the bending of starlight to explaining the orbit of Mercury. But we've never been able to test it rigorously across the entire history of the universe. Perhaps gravity behaves slightly differently over cosmic distances and timescales than it does within our solar system. A modified gravity theory could affect how structures form and how the expansion rate evolves, potentially explaining why the early and late measurements don't match. This wouldn't mean throwing out Einstein's work, but rather refining it for a cosmological context, much like Einstein refined Newton's laws. There are other, even more exotic proposals. Some theorists suggest that our region of the universe is part of a vast underdensity, a cosmic void, that is expanding faster than the average, making our local measurements unrepresentative of the whole cosmos. Others explore the idea that dark matter might have unusual properties, interacting with itself or with light in ways we haven't accounted for. What's fascinating is that each of these proposals, while designed to solve the Hubble tension, would have sweeping implications far beyond this single number. Discovering early dark energy would revolutionize our understanding of the universe's infancy. Modifying gravity would reshape fundamental physics. Finding that we live in a special void would challenge the cosmological principle itself. For years, the Hubble tension was often downplayed or attributed to systematic errors in the measurements. But as the data has improved from observatories like the Planck satellite and the Hubble Space Telescope, the discrepancy has only become more significant and harder to ignore. It has graduated from a potential problem to a genuine clue, a signal from the universe that our current models are a good first approximation, but not the final word. This tension is more than just a conflict in data. It's an invitation to explore, a signpost pointing toward a deeper and more complex cosmic history than we had ever assumed. By embracing this discrepancy rather than explaining it away, we open the door to discoveries that could fundamentally alter our story of the cosmos. While we often look to the distant cosmos for mysteries, some of the most intriguing clues have emerged much closer to home, hidden in the precise orbital mechanics of our own robotic explorers. As spacecraft like Galileo and Rosetta swung past Earth to gain a gravitational boost for their long journeys to Jupiter and a comet, navigators noticed something peculiar. These meticulously planned gravity assists, which work like a cosmic slingshot using a planet's gravity to accelerate or change a probe's trajectory, came with a tiny but consistent error. Each time, the spacecraft emerged from Earth's shadow with a velocity slightly different from what our best models predicted. A deviation of just a few millimeters per second, an amount so small it seems trivial, but in the high-precision world of orbital dynamics, it was a glaring anomaly that refused to go away. Initially, engineers attributed these flyby anomalies to mundane effects they knew could influence a spacecraft's path. The gentle but constant push of solar radiation pressure, for instance, or the faint whisper of Earth's outer atmosphere, which, even at high altitudes, can impart a minuscule amount of drag. But as the data from multiple flybys by Galileo, Near, Rosetta, and others accumulated, a pattern emerged. After accounting for every known force with painstaking precision, a residual anomaly remained. It was a consistent, unmodeled nudge that seemed to occur specifically during the closest approach to Earth. This wasn't a random error, it was a signal, a tiny echo of physics that our equations weren't capturing. What makes this clue so compelling is its potential connection to the most fundamental laws of nature. Some physicists have proposed that these anomalies could be a hint of modified inertia, a suggestion that our understanding of how objects respond to forces, rooted in Newton's laws and refined by Einstein, might need adjustment under certain conditions. This idea, known as modified Newtonian dynamics or MUND, was originally proposed to explain galactic rotation curves without dark matter, but it also predicts subtle effects on accelerating bodies that could manifest during a planetary flyby. If the flyby anomaly is a validation of this, it would represent a seismic shift in physics, suggesting that inertia itself is not an absolute property, but can be influenced by the surrounding mass distribution, a concept that echoes the controversial but intriguing Mach's principle. Another tantalizing possibility is that the spacecraft are briefly passing through localized clouds of dark matter. We typically think of dark matter as halos surrounding galaxies, but it could also be clumped into finer streams and filaments throughout the solar system. If a spacecraft were to traverse a region with a slightly higher density of this invisible material, its gravitational pull could impart just enough of a velocity change to account for the anomaly. This would turn our planetary flybys into an unexpected and powerful tool for mapping the distribution of dark matter right here in our own cosmic neighborhood, using humanity's fleet of interplanetary probes as sensitive detectors for the unseen. There are even more exotic theories involving the Earth's rotation and its gravitational field. Some models suggest that the anomaly might be linked to the planet's angular momentum, with the spinning mass of Earth creating a subtle, previously unaccounted for gravitomagnetic effect that tugs on the spacecraft. This would be a manifestation of Einstein's general relativity, but in a regime so subtle that we haven't been able to test it until now with these incredibly precise flyby operations. The true power of this clue lies in its testability. Unlike mysteries buried in ancient light from quasars or the faint whispers of the cosmic microwave background, the flyby anomaly is a phenomenon we can actively probe. We can design future missions with enhanced tracking using dedicated radar systems or laser ranging to measure their trajectories with even greater precision during Earth flybys. By analyzing the exact timing and magnitude of the velocity change, we could distinguish between different potential causes. Does the anomaly depend on the spacecraft's orientation? Does it vary with the latitude of the flyby? Each detail is a piece of the puzzle. This ongoing investigation serves as a profound reminder that groundbreaking discoveries aren't always made in the depths of space. Sometimes they are hiding in the margins of our own engineering data, in the tiny discrepancies between prediction and observation that we might otherwise dismiss as noise. The Flyby anomaly challenges the notion that we completely understand the physics of our own backyard. It suggests that even the well-trodden path around our home planet still holds secrets, and that by paying close attention to the subtle whispers of our own spacecraft, we might just hear the faint echo of a new law of physics. For decades, astronomers have observed a strange and relentless cosmic current, a mysterious gravitational pull that is drawing our entire Milky Way galaxy, along with countless others, through the void at an astonishing speed of over 600 kilometers per second. This invisible force has been dubbed the Great Attractor, and it represents one of the most profound gravitational mysteries in our local universe. The problem is, we can't actually see what's doing the pulling. The Great Attractor lies in a direction almost exactly behind the center of our own galaxy, a region shrouded from optical view by thick clouds of gas and dust, countless stars, and the brilliant glare of the Milky Way's bulge. This area is known as the Zone of Avoidance, and for a long time it was a literal blind spot in our maps of the cosmos, a place where conventional telescopes simply couldn't peer. Early attempts to understand this gravitational anomaly were like trying to identify a mountain by feeling the slope of the land while standing in a dense fog. We knew something massive was there by its effect on our motion, but its true nature was completely hidden. Initial theories proposed it was a massive concentration of mass, perhaps a supercluster of galaxies so immense that its gravity was dictating the motion of our entire local galactic neighborhood. But without being able to see it, the Great Attractor remained a ghost in the machine, a compelling idea that was frustratingly out of reach. This clue was largely set aside not because it wasn't important, but because the technological means to investigate it simply didn't exist yet. It was an echo of a hidden structure, a gravitational whisper we could detect but not decipher. The breakthrough began when we learned to see the universe in new light, literally. Infrared and radio telescopes have the remarkable ability to pierce through the cosmic dust that blocks visible light. Instruments like NASA's Spitzer Space Telescope and the Parkes Radio Telescope in Australia began to map the sky in these wavelengths, effectively lifting the veil on the zone of avoidance. What they revealed was astonishing. There wasn't just one massive structure, but an even larger cosmic environment now known as the Laniakea supercluster, of which our own local group of galaxies is just a small part. The Great Attractor appears to be the gravitational center of this vast supercluster, a node in the cosmic web where filaments of galaxies converge onto a central point of immense density. But the story doesn't end there. Even with this newfound understanding, some measurements suggest that the sheer amount of visible mass in the Laniakea supercluster might still not be sufficient to account for the full strength of the gravitational pull we experience. This opens the door to an even more intriguing possibility, that the Great Attractor is not just a collection of galaxies we can now see with better telescopes, but that it might also be a concentration of something darker. It could be a focal point for dark matter, the invisible substance that makes up most of the universe's mass, whose gravitational influence is felt but whose nature remains one of physics' greatest secrets. The pull we feel could be the combined force of thousands of galaxies and an even more massive halo of this mysterious dark material, woven together in a knot of cosmic gravity. This transforms the Great Attractor from a simple mystery into a profound clue. It's no longer just about finding a missing group of galaxies. It's about understanding the architecture of the universe on the largest scales. The gravitational flows that guide the motion of galaxies are like cosmic rivers, and by mapping their currents, we can trace them back to their sources, the mountains of mass that shape the entire landscape of the cosmos. The Great Attractor is one of the largest of these mountains in our vicinity, and studying it helps us understand how matter, both seen and unseen, is distributed throughout the universe. What makes this clue so powerful is its demonstration of how our perspective shapes our understanding. For a century, we viewed the universe from our limited vantage point, mapping what we could see with our eyes and optical instruments. The zone of avoidance was a reminder of our own cosmic parochialism, a blank spot on the map that hid a fundamental truth about our place in the universe. By developing new ways to see, we didn't just fill in that blank spot. We discovered that our home is part of a structure far grander than we had ever imagined. The Great Attractor is a testament to the fact that the most significant forces in the universe are often hidden, waiting for our curiosity and ingenuity to finally bring them into focus. Now let's turn our attention to a mystery much closer to home, one that reaches back to the very dawn of our planet and challenges our understanding of how life managed to gain a foothold in what should have been a deeply hostile environment. This is the faint young sun paradox, a puzzle that has intrigued astronomers and geologists for decades. Here's the core of the problem. Based on our well-established models of stellar evolution, we know that stars like our sun grow brighter as they age. Billions of years ago, when life first appeared on Earth, the sun was significantly dimmer, about 20 to 30% less luminous than it is today. According to straightforward physics, that reduced energy output should have meant a completely frozen Earth, a global snowball with average temperatures well below the freezing point of water. And yet, the geological record tells a completely different story. Ancient rocks from that era, some over 3.8 billion years old, show clear evidence of liquid water, sedimentary deposits, pillow lavas that form underwater, and minerals that can only exist in a liquid water environment. Even more strikingly, there is isotopic evidence in the oldest zircons pointing to a hydrous crust and interactions with liquid water. The planet was not only unfrozen, it was warm enough for life to emerge and thrive. The standard solution to this paradox, and the one you'll find in most textbooks, invokes a powerful greenhouse effect. The idea is that Earth's early atmosphere must have been rich in potent greenhouse gases like methane and carbon dioxide, trapping enough of the sun's faint heat to keep the planet temperate. This is a perfectly reasonable explanation, and there is evidence to support it. Volcanic activity was likely more intense on the young, hotter Earth, pumping vast quantities of carbon dioxide into the air. Furthermore, before the rise of oxygen-breathing life, methane-producing microbes may have dominated, filling the atmosphere with a gas that is incredibly effective at trapping heat. This scenario paints a picture of a planet swaddled in a thick, insulating blanket of gases, compensating for the weak sunlight. But what if that's not the whole story? What if we've been leaning so heavily on the greenhouse gas explanation that we've overlooked other, more subtle clues embedded in this ancient cosmic echo? One fascinating alternative revolves around the sun itself. Our models of stellar evolution are robust, but they are based on the behavior of the sun as we observe it today, a relatively stable, middle-aged star. The young sun, however, might have been far more volatile. It could have been subject to frequent and powerful solar flares, eruptions that would have hurled immense amounts of high-energy radiation and particles toward the early Earth. While this might sound destructive, this intense activity could have had a warming effect. These particles could have catalyzed chemical reactions in the upper atmosphere, producing nitrogen oxides that are also potent greenhouse gases, effectively helping to build that protective blanket. Alternatively, a stronger solar wind might have compressed Earth's magnetic field less frequently, allowing our planet to retain a thicker atmosphere for longer, which would also enhance heat retention. Another underexplored clue involves Earth's own internal engine. The planet's magnetic field, generated by the churning of its molten iron core, is our shield against the erosive force of the solar wind. There is evidence to suggest that Earth's magnetic field was significantly stronger in the distant past. A more powerful magnetosphere would have been even more effective at deflecting solar wind, preventing the stripping away of our atmosphere. If the early atmosphere was denser and remained intact for longer due to this powerful magnetic shield, the greenhouse effect would have been that much more efficient, easily resolving the paradox. This turns the spotlight away from the atmosphere alone and toward the dynamic, deep Earth processes that are often forgotten in this conversation. There's also the intriguing role of Earth's surface itself. The young planet had far less continental landmass. The world was predominantly a water-covered sphere with scattered volcanic islands. A darker, ocean-dominated surface would have absorbed more of the sun's incoming radiation than a brighter, continent-covered one, which reflects more light back into space. This lower albedo or reflectivity would have contributed to global warming. Furthermore, the specific types of clouds in the ancient atmosphere, their composition and altitude, could have had a net warming effect rather than a cooling one, another factor that is incredibly difficult to model over billion-year timescales but could have played a decisive role. This paradox is far more than an academic curiosity about our own planet's past. It's a profound clue that resonates through our search for life beyond Earth. When we look at distant exoplanets orbiting other stars, we use models of stellar evolution and planetary climate to determine their potential habitability. The faint young sun paradox is a stark reminder that those models might be incomplete. If our own planet found a way to be habitable under conditions that our basic physics says should have been fatal, then how many other worlds orbiting other faint young stars might also be harboring life against all odds? It challenges the very definition of the habitable zone, suggesting that a planet's fate isn't sealed solely by its distance from its star. Factors like planetary magnetism, atmospheric composition, geological activity, and even the star's own youthful volatility can conspire to create conditions ripe for life where none should logically exist. By re-examining this ancient echo from our solar system's youth, we aren't just solving a puzzle about Earth, we are learning how to listen for the whispers of resilience on worlds we have yet to discover. While we often focus our most powerful telescopes on the depths of the cosmos, some of the solar system's most persistent and puzzling clues have been flickering right above our heads for centuries, visible to anyone with a basic telescope and a patient eye. These are transient lunar phenomena, or TLP, mysterious, fleeting flashes of light, colored glows, and obscurations that appear and vanish on the surface of the moon. Historical records from astronomers as far back as the 18th century document these strange events: sudden brightenings in the crater Plato, reddish hazes clouding the interior of Alphonsus, or brief, star-like points of light that ignite and then disappear into the gray landscape. For a long time, the conventional wisdom dismissed these reports as tricks of the eye, atmospheric distortion, or the predictable glint of sunlight hitting a mountain peak at just the right angle. But a closer look at the data reveals a more compelling story, one that suggests these aren't mere illusions but real events, and that they might be whispering secrets about a moon that is far more dynamic than its silent, barren appearance suggests. What separates potential signal from mere noise is the pattern within the chaos. While some flashes are undoubtedly meteorite impacts, a common occurrence on the airless moon, many documented TLP events don't fit that profile. Impact flashes are instantaneous, like a camera flash, and are over in a fraction of a second. But numerous reliable observations, including some by Apollo astronauts orbiting the moon, describe glows that persist for minutes or even hours, along with gradual changes in surface coloration and temporary, localized hazes. These aren't the signatures of a random space rock strike. They point to processes emanating from the moon itself. The most compelling hypothesis is that we are witnessing outgassing, the release of trapped gases from deep beneath the lunar surface. The moon was once a volcanic world, and while its large-scale volcanic activity ceased billions of years ago, it might still possess residual heat and pockets of volatile substances like radon gas. A sudden release of this gas, perhaps triggered by tiny moonquakes or the tidal flexing caused by Earth's gravity, could carry fine dust particles to the surface, creating a temporary, shimmering cloud that scatters sunlight and produces a faint, ethereal glow. Another fascinating possibility involves the moon's exotic electrostatic environment. Without an atmosphere to moderate the extreme temperature swings between day and night, the lunar surface becomes electrically charged. During the long lunar day, solar ultraviolet radiation knocks electrons loose from the soil, giving it a positive charge. As the sun sets, this charge can create intense electrostatic fields. Some scientists theorize that this could lead to phenomena like electrostatic levitation, where fine dust particles float above the surface, or even to tiny electrical discharges, essentially silent, miniature lightning strikes within the dust itself. These events could generate brief, localized flashes of light, a kind of weather unique to airless worlds. This wouldn't be a geological process in the traditional sense, but a geophysical one, a reminder that even a dead world can have a kind of life thrumming across its surface. The true significance of these transient events isn't just in explaining a curiosity. It's in what they could reveal about the moon's hidden resources and its violent history. If outgassing is real, the gases being released could tell us about the moon's interior composition and whether it still holds valuable reservoirs of water ice or other volatiles trapped in permanently shadowed craters. For future lunar exploration and potential colonization, knowing where and how these gases are released is practically essential. It could point the way to sources of water for life support or hydrogen for rocket fuel. Furthermore, understanding this activity provides a window into the solar system's past. The moon is a museum, its surface largely unchanged for eons. If it is still subtly active, it means we are witnessing the faint, final echoes of the powerful geological forces that shaped all the rocky worlds early in their history. By studying these whispers on the moon, we might better understand the early volcanic activity on Mercury, Mars, or even distant icy moons. Despite their potential importance, transient lunar phenomena have never been studied with the rigorous, sustained effort they deserve. They are unpredictable, fleeting, and difficult to capture with telescopes that are often tasked with looking at objects millions of light years away. This has left the field peppered with anecdotal reports but lacking the hard, statistical data needed for a scientific breakthrough. That, however, is beginning to change. Projects like the European Space Agency's Neliota system are now using dedicated telescopes to continuously monitor the moon's dark side, automatically detecting and classifying impact flashes. While focused on impacts, this technology could easily be adapted to search for the longer duration glows that signify TLP. Imagine a global network of lunar monitoring stations, armed with high-resolution cameras and spectrometers, watching the moon's every move. Such a project could finally create a definitive catalog of these events, mapping their locations and timing to see if they correlate with known moonquake zones, tidal stresses, or specific geological features. By finally giving these lunar whispers the attention they warrant, we might do more than just solve a centuries-old mystery. We could be learning the language of a world we think we know, discovering that it still has stories to tell about its fiery birth, its slow cooling, and the resources it holds in reserve for the next generation of explorers. These faint flashes in the darkness are a reminder that sometimes the most profound clues aren't found in the distant cosmos, but on the familiar face of our nearest celestial neighbor, waiting for us to look just a little closer. Stretching across vast tracts of the night sky, immense arcs of radio energy curve through the void like the ghostly ribs of a cosmic beast. These are the galactic radio loops, and they represent one of the most spectacular yet enigmatic features of our home galaxy's architecture. The most famous of these, the North Polar Spur, is so enormous that it dominates the radio sky in the northern hemisphere, a colossal plume of emission that seems to billow upward from the galactic center. For decades, the standard explanation for these structures has pointed to the aftermath of stellar death, supernova remnants. The logic is sound. When a massive star explodes, it blows a bubble of hot, magnetized plasma into the surrounding space, and the shock waves from such an event can accelerate electrons to nearly the speed of light. As these relativistic electrons spiral along magnetic field lines, they emit synchrotron radiation, the very type of radio waves we detect from these loops. It's a tidy, well-understood process, and in many cases it's almost certainly correct. But a closer look at the largest and most energetic loops reveals details that don't quite fit the standard supernova narrative, hinting at forces far more powerful and mysterious than a single star's final act. The problems with the simple supernova explanation become apparent when we examine the sheer scale and energy of these structures. The North Polar Spur, for instance, isn't just a local feature. It stretches over a significant portion of the sky, implying a physical size that could encompass thousands of light years. To create a structure that vast, you wouldn't need just one supernova, you'd need a whole series of them, a coordinated chain of explosions occurring in the same region over millions of years. This is not impossible. Stars are often born in clusters and can die in clusters as well. But even this scaled-up model, known as a superbubble, struggles to account for the precise morphology and incredible energy of the most pronounced loops. Their smooth, coherent arcs and the intensity of their polarized emission suggest a single, cataclysmic event rather than a protracted sequence of smaller ones, pushing astronomers to consider more exotic and dramatic origins. One compelling alternative is that we are witnessing the echo of a galactic wind, a vast outflow of material driven not from a single point, but from the collective fury of star formation across the entire central region of the Milky Way. In this scenario, the combined energy of thousands of supernova and the powerful stellar winds from massive stars in the galactic center could have launched a bipolar outflow, a torrent of hot gas that punches its way out of the galactic disk and into the halo. The radio loops we see could be the shock fronts from this outflow, where the material slams into the thinner gas of the galactic halo, creating immense, standing waves of energy that persist for eons. This would connect them to the overall feedback cycle of the galaxy, where periods of intense star formation ultimately shut themselves down by blowing away the very gas clouds that fuel them. Perhaps the most intriguing and radical hypothesis involves dark matter. If certain theoretical particles that make up dark matter, such as WIMP, can interact with each other and annihilate upon collision, these annihilations would release a torrent of energy and produce standard particles like electrons and positrons. A dense concentration of dark matter in the galactic center or halo could therefore act as a powerful particle accelerator, generating the very relativistic electrons that create synchrotron radiation in magnetic fields. A giant radio loop could, in theory, be a visible map of where a clump of dark matter is currently being annihilated, or where it was annihilated in the distant past. While this remains a speculative idea, it's a tantalizing possibility that turns these radio echoes into a potential window into the invisible substance that governs the cosmos. What makes these structures such a rich source of clues is not just their origin, but the information encoded within their light. The radio emission from these loops is highly polarized, meaning the waves are aligned in a specific direction. This polarization is a direct tracer of the magnetic fields that permeate the structure. By meticulously mapping the polarization angles across a loop, astronomers can effectively chart the magnetic field lines, revealing how these fields are stretched, compressed, and twisted by the immense forces that shaped the loop. This gives us a unique opportunity to understand the role of magnetism on galactic scales, a force that is incredibly difficult to study, but is crucial for shaping the evolution of galaxies, controlling the collapse of gas clouds into stars, and channeling the cosmic rays that constantly bombard our solar system. Despite their significance, the galactic radio loops have often been overlooked in large-scale surveys. Their very size works against them. They are so expansive that they can be difficult to capture in high resolution with telescopes designed to focus on smaller, point-like objects. They become background features, subtracted out as noise in studies focusing on more compact sources. It's a classic case of not seeing the forest for the trees, where these gigantic cosmic landmarks are filtered out in the search for finer details. Only with the advent of sophisticated, wide-field radio telescopes and all-sky surveys are we beginning to appreciate the full complexity and importance of these structures. They are not mere fossils, they are active, dynamic features that continue to shape the environment of our galaxy, influencing the path of cosmic rays and the evolution of gas clouds that may one day form new stars. By finally giving these radio echoes the attention they deserve, we are listening to the reverberations of the Milky Way's most violent outbursts, slowly deciphering the story of how our galaxy came to be and what forces continue to churn within its heart. But the search for the tetraneutron is more than just a quest for a new particle. It's a direct probe into the nature of the universe's most fundamental forces. The strong nuclear force which binds protons and neutrons together in atomic nuclei is incredibly powerful but operates over vanishingly small distances. It's a delicate balance of attraction and repulsion, and our current models, based on interactions between pairs of nucleons, cannot easily accommodate a stable, multi-neutron cluster. A confirmed tetraneutron would force a dramatic rewrite of these models, suggesting the existence of previously unknown multi-neutron interactions, or even a new, short-range aspect of the strong force itself. This wouldn't just change a footnote in a textbook, it would reshape our understanding of how all matter is constructed at its core. The implications of such a discovery would ripple far beyond the laboratory, echoing into some of the most extreme environments in the cosmos. Consider the neutron star, the ultra-dense corpse of a massive star. These cosmic objects are essentially giant atomic nuclei, but on a scale miles wide. Their immense gravity squeezes matter together so tightly that the boundaries between individual nuclei break down, creating a bizarre quantum soup often referred to as neutron star matter. The properties of this matter, its density, its viscosity, its ability to conduct heat are dictated by the complex interactions between neutrons. If a tetraneutron or even larger neutron clusters can form under less extreme conditions here on Earth, it suggests that the interior of a neutron star might be even more complex and stratified than we currently imagine. These superfluids could contain a zoo of exotic, temporary particles that influence how the star cools, how it behaves during starquakes, and even how it spins. A tiny echo in a particle accelerator could therefore help us decipher the inner workings of these cosmic powerhouses. This clue is a perfect example of how the universe's whispers aren't always found in distant telescopes. Sometimes they manifest in the precise, controlled chaos of a laboratory experiment. The initial signals for the Tetra neutron were faint, buried in statistical noise, and often dismissed as artifacts because they challenged a deeply held paradigm. It's a recurring theme in science, the tendency to categorize the unexpected as an error rather than an opportunity. But with the advent of new, more powerful particle accelerators and sophisticated detection systems, we are now in a position to revisit these anomalies with the rigor they deserve. Experiments can now be designed to specifically hunt for these resonant states, using beams of unstable nuclei to carefully probe the forces that might allow such an entity to exist, even for a fleeting moment. The pursuit of the tetraneutron is a testament to the idea that no data point is too small to ignore, and no theory is too sacred to challenge. It demonstrates that the same curiosity that drives us to look at the farthest reaches of the cosmos can be applied to the smallest scales of existence, and that a breakthrough in one realm can illuminate the other. Whether the tetraneutron is finally confirmed or ruled out, the very act of searching for it pushes the boundaries of technology and theory, reminding us that the next great discovery might not be hidden in the depths of space, but in the subtle, overlooked details of an experiment conducted right here on Earth. Imagine the entire observable universe, all 93 billion light-years of it, not as a static expanse but as a river with countless galaxies floating on its currents. Now imagine that astronomers, by meticulously tracking the motion of massive galaxy clusters, discovered something that defies all logic. These clusters aren't just drifting apart with the expansion of space. They are also all flowing in the same specific direction, like leaves caught in a cosmic tide. This mysterious, coordinated motion is what scientists call dark flow, and its implications are so profound that they hint at forces operating from beyond the very edge of everything we can see. The story of dark flow begins with the cosmic microwave background, the ancient light from the Big Bang. This radiation fills the universe and provides a fixed reference frame, a backdrop against which all motion can be measured. By studying subtle distortions in this background light caused by the movement of massive galaxy clusters, an effect known as the kinematic Sunyaev-Zeldovich effect, a team of researchers led by Alexander Kashlinsky made an astonishing claim in 2008. They found evidence that hundreds of clusters were all streaming toward a particular point in the sky near the constellations Centaurus and Vela at speeds of nearly 1,000 kilometers per second. This motion was separate from the Hubble expansion. It was a peculiar velocity on a gargantuan scale, and it shouldn't have been there according to our standard model of cosmology, which assumes the universe is largely uniform and isotropic on the largest scales. Unsurprisingly, the initial claim was met with intense skepticism and controversy. Many in the scientific community argued that the signal was a statistical fluke, an artifact of incomplete data or unaccounted for systematic errors. Some studies using different methodologies seemed to debunk the idea entirely, and for a time, dark flow was relegated to the fringes of cosmology, a curious anomaly that was probably explained away. But like a stubborn whisper that refuses to be silenced, the signal persisted. Newer, more precise analyses, including some using data from the Planck satellite, have continued to find evidence of a residual bulk flow, a coordinated motion that extends out to distances of billions of light-years. While the measured speed may be lower than first reported, the fact that any such flow exists at all on these scales is deeply problematic for our current understanding. If dark flow is real, its explanation must be as extraordinary as the phenomenon itself. The most mind-bending possibility is that the flow is caused by the gravitational pull of something immense that lies beyond our cosmological horizon, beyond the limit of what we can ever hope to observe because the space between it and us is expanding faster than light can travel. This couldn't be just another galaxy or even another supercluster. The structure would have to be unimaginably vast, a concentration of mass so enormous that its gravity can tug on entire swaths of our visible universe. This idea shatters the foundational cosmological principle, which states that the universe should look roughly the same in every direction and from every location. It suggests that our universe is not uniform after all, but is part of a much larger and more varied structure. This leads to another breathtaking explanation. That dark flow could be an echo from the era before cosmic inflation, a relic of the initial conditions of the universe. Perhaps the seeds of this flow were planted in the first fractions of a second after the Big Bang, during a period of ultra-rapid expansion that somehow imprinted a preferred direction on the fabric of spacetime itself. Alternatively, the flow might be evidence of a collision with another universe in the multiverse. In some multiverse theories, our universe is one bubble in a vast cosmic foam, and it's possible that our bubble grazed against another, an interaction that could have set everything within our cosmic horizon moving in a coordinated direction. This isn't just speculation about unseen mass, it's speculation about unseen realities, other entire universes exerting their influence on our own. The true power of this clue lies in its audacious challenge to our perspective. For centuries, we've assumed that what we can see is, for all intents and purposes, the entire playing field. Dark flow suggests that we are merely a small part of a far grander structure, and that the forces which shape our cosmic destiny may originate in realms we can never directly observe. It transforms the universe from a self-contained entity into what might be just one province of a much larger, and possibly infinite, metaverse. By continuing to study these subtle gravitational currents, we are not just mapping the motion of galaxies, we are perhaps, for the first time, feeling the pull of the unknown that lies beyond the limits of our own universe. Now let's rewind the cosmic clock all the way back to the very first minutes of existence, to a time when the entire universe was a seething, dense fusion reactor, forging the first atomic nuclei in a process we call Big Bang nucleosynthesis. Our models of this primordial alchemy are spectacularly successful. They accurately predict the observed cosmic abundances of the lightest elements, hydrogen, helium, and their isotopes. But there is one stubborn, glaring exception, a single note that's been out of tune for decades. According to our most precise calculations, the universe should have created about 3 times more lithium-7 than we actually find when we look at the oldest stars in our galaxy. This isn't a small margin of error, it's a factor of 3 discrepancy, a cosmic accounting problem that has persisted through every refinement of our theories and observations. We call this the lithium problem, and it's a quiet but profound echo from the dawn of time, suggesting that our story of the universe's first moments is still missing a few crucial pages. The standard solution has been to blame the stars themselves. The logic goes that these ancient, metal-poor stars, the very ones we use as cosmic time capsules because their atmospheres reflect the composition of the early galaxy, might have internal processes that slowly destroy lithium over their multi-billion-year lifetimes. Conveyor belts of plasma could drag lithium from the surface down into the scorching interiors where it is fused into heavier elements, effectively scrubbing it from the outer layers we can observe with our telescopes. It's a reasonable and physically plausible explanation, a stellar sleight of hand that would resolve the inconsistency. But as astronomers have looked closer, this convenient answer has begun to fray at the edges. For instance, the amount of lithium depletion doesn't seem to correlate perfectly with other factors like a star's temperature or metallicity in ways the models predict. Some stars show the expected low levels, but others, with seemingly identical properties, do not. This lack of a clear, consistent pattern suggests that while stellar processing might be part of the story, it's unlikely to be the whole story. There's a lingering suspicion that the problem wasn't created in the stars but was delivered to them, a relic of a fundamental error in our understanding of the universe's first few minutes. This opens the door to far more exciting and radical possibilities. What if the lithium problem isn't an astronomical error but a particle physics one? The nuclear reactions that forged lithium are exquisitely sensitive to the conditions of the early universe, its density, temperature, and the specific rates at which protons and neutrons crashed together and fused. If something was subtly different during that brief, fiery epoch, it would leave an indelible mark on the elemental abundances we see today. One compelling idea is that an unknown type of particle was present, interacting with the primordial soup and altering the reaction pathways. Certain proposed candidates for dark matter, like weakly interacting massive particles, could have been decaying or annihilating during nucleosynthesis, injecting just enough extra energy into the mix to disrupt the delicate chain of reactions that leads to lithium-7, suppressing its final yield. In this scenario, the lithium deficit isn't a problem to be solved. It's the first faint signal of dark matter revealing its properties through an event that occurred 13.8 billion years ago. Another fascinating line of thought challenges the very assumption of a smooth, homogeneous early universe. Our standard models presume that matter and energy were distributed with near-perfect uniformity after inflation. But what if there were tiny, residual fluctuations in density or temperature on very small scales? These inhomogeneities could have created localized pockets where nuclear fusion proceeded at slightly different rates, leading to an overall blend of elements that doesn't match the predictions of a perfectly smooth model. It's like assuming a cake batter is perfectly mixed. If there are small pockets of unmixed flour or sugar, the final taste won't match the recipe, even if all the ingredients are correct. If true, this would mean our universe's infancy was a bit lumpier than we thought, a subtle complexity that has been hiding in plain sight within the lithium content of ancient stars. The pursuit of this clue is pushing observational astronomy to its limits. Scientists are no longer just looking at a handful of old stars. They are conducting vast, systematic surveys, measuring lithium abundances in thousands of stars across the galaxy, searching for patterns and correlations that might point to a solution. They are also looking beyond our galaxy, using the most powerful telescopes to measure lithium in the diffuse gas between galaxies, and even in the atmospheres of the most pristine, ancient gas clouds, which should be completely untouched by any stellar processing. Each new measurement is a vote, helping to determine whether the lithium problem was born in the stars or in the Big Bang itself. This tiny discrepancy in the amount of a single element is a powerful lesson in scientific humility. It reminds us that even our most successful and well-tested theories can still harbor deep mysteries. The Big Bang model is a triumph of modern cosmology, but the lithium problem is its persistent, unanswered whisper, a hint that the universe's opening chapter might have contained plot twists we are only now beginning to imagine. By listening to this faint echo from the first 3 minutes, we aren't just solving a puzzle about lithium. We are probing the fundamental laws of physics and the very conditions of existence at the beginning of everything. These stellar explosions are the workhorses of modern cosmology, trusted mile markers that we use to chart the expansion history of the universe itself. Their reliability stems from a seemingly straightforward origin story. A white dwarf star, the dense cinder of a sun-like star, steals material from a companion until it reaches a critical mass threshold, triggering a thermonuclear inferno that incinerates it completely. Because this detonation always happens at roughly the same mass, the resulting supernova always shines with a predictable peak brightness. By comparing this intrinsic brightness to how dim it appears from Earth, astronomers can calculate its distance with remarkable precision. It was this very method that revealed the universe's accelerating expansion, a discovery that earned the Nobel Prize and introduced the world to the mystery of dark energy. Our entire cosmic distance ladder, and by extension our model of the cosmos, leans heavily on the assumption that these explosions are uniform and predictable. But a growing catalogue of peculiar type Ia supernova is whispering a different, more complex story. Not all of these cosmic blasts are created equal. Some take an unusually long time to fade away, while others dim far too quickly. Their colors can vary, with some appearing redder or bluer than the standard template. For years, the instinct was to treat these oddballs as outliers, statistical noise to be filtered out of the clean datasets used for precise cosmological measurements. The goal was to find the perfect standard candles, so the imperfect ones were often set aside. But in doing so, we may have been ignoring vital clues about the true nature of these explosions. These aren't errors, they are echoes of diversity, hints that the pathway to a type Ia supernova is not a single monolithic process, but rather a family of related events. The key to understanding this diversity lies in the progenitor systems, the specific setup that leads to the explosion. The classic image is a white dwarf and a main sequence star like our Sun, locked in a closed dance. But what if the donor star is a red giant, pouring a different kind of fuel onto the white dwarf at a different rate? What if the explosion is triggered by the merger of two white dwarfs, a violent collision that would create a vastly different explosive environment compared to a single dwarf slowly accreting mass? Each of these scenarios would produce a supernova with a distinct signature, a slightly different light curve, a unique chemical fingerprint in its spectrum, or a change in how its brightness evolves over time. The peculiar supernova we observe could be the representatives of these rare progenitor channels, each telling a different story about the final moments of binary star systems. Beyond stellar demographics, these anomalies might also be pointing toward physics we haven't yet accounted for. The nuclear flame that tears through a white dwarf is a complex phenomenon, and its propagation could be influenced by factors we are only beginning to understand. The composition of the white dwarf itself is crucial. A star with a higher carbon-to-oxygen ratio might burn differently than one with a lower ratio. The strength and configuration of the magnetic field entombed within the dwarf could also alter the explosion, creating asymmetries that make the supernova appear brighter or dimmer depending on the angle from which we view it. It's even possible that exotic particles or unknown aspects of nuclear physics play a role in how the detonation unfolds, leaving a subtle imprint on the light we receive. The imperative to embrace these peculiarities is about more than just scientific curiosity. It's about ensuring the accuracy of our entire cosmic map. If we are using a ruler that has subtle, uncalibrated variations, our measurements of the universe's expansion will contain hidden errors. By meticulously studying the outliers, by classifying their unique light curves and spectra, we can actually improve our distance measurements. We can learn to recognize the specific patterns that signal a tweaked standard candle and adjust our calculations accordingly. This turns a problem into a solution, transforming anomalies into refinements that sharpen our view of dark energy and the ultimate fate of the cosmos. Each unusual flash in the night sky is an invitation to listen more closely to the complex and varied ways stars meet their end, reminding us that nature rarely follows a single, simple script. Imagine a galaxy that holds the mass of our own Milky Way with its hundreds of billions of stars, its majestic spiral arms, and its brilliant, glowing core. Now picture that same immense gravitational pull, the same vast reservoir of dark matter, but remove almost all of the stars. What you're left with is a ghost, a vast, dark, and almost empty structure drifting through the cosmic web. This is the reality of ultra-diffuse galaxies like Dragonfly 44, and their existence is one of the most perplexing clues challenging our understanding of how galaxies are born and why they evolve the way they do. Discovered only within the last decade, these spectral objects were hiding in plain sight for so long precisely because they are so faint. Their starlight is spread so thin that they blend almost seamlessly into the background glow of the night sky. It took a special kind of telescope, one with exceptionally low surface brightness capabilities, like the Dragonfly telephoto array, to finally pull them into focus. Once we knew how to look, we found them in surprising numbers, particularly within massive galaxy clusters like Coma. And with that discovery came an immediate and profound mystery. When astronomers measured the motions of the few stars within Dragonfly 44, they found they were orbiting at tremendous speeds, indicating the presence of a huge amount of gravitational force. The conclusion was inescapable. This faint, wispy galaxy possesses a dark matter halo as massive as our own Milky Ways. How does a galaxy acquire and retain such an enormous amount of dark matter while failing so spectacularly at the one thing galaxies are supposed to do, form stars? This contradiction strikes at the very heart of galaxy formation theory. The standard model suggests that dark matter halos form first, acting as gravitational wells that pull in vast amounts of gas. This gas then cools, condenses, and eventually fragments to ignite star formation. In this story, a massive dark matter halo should inevitably lead to a massive, bright galaxy. Ultra-diffuse galaxies break this chain. They have the massive halo, but the star formation process was somehow switched off almost entirely, or never began in earnest to start with. This forces us to consider that the environment a galaxy lives in plays a far more brutal and decisive role than we previously thought. One compelling explanation is that these galaxies are ancient relics, born in the early universe, but then thrust into the harsh environment of a dense galaxy cluster. As a young galaxy falls into a cluster, it can be subjected to a process known as ram pressure stripping. The space between galaxies in a cluster isn't empty, it's filled with a hot, thin plasma. As a galaxy plows through this intracluster medium at millions of miles per hour, the resistance can be so intense that it literally strips the galaxy of its star-forming gas, like wind blowing dust off a table. The galaxy's dark matter halo, which is spread out and doesn't interact with the plasma, remains untouched. The result is a massive dark matter anchor with just a faint whisper of stars left behind, a galaxy that had its potential for brilliance violently quenched. But what about the ultra-diffuse galaxies found in isolation, far from the punishing forces of a cluster? Their existence suggests another, perhaps even more intriguing possibility. Maybe these galaxies were born in an unusual way, from gas that was simply too hot or too turbulent from the very beginning to collapse efficiently into stars. Or perhaps their dark matter halos have a specific, smoother structure that provides a weaker gravitational pull on incoming gas, preventing it from reaching the densities needed for widespread star birth. These scenarios paint a picture of a universe where the path to becoming a galaxy is not a single, guaranteed highway, but a branching tree of possibilities, with some roads leading to dazzling cities of light and others to dark, quiet towns. The most radical interpretation of all is that ultra-diffuse galaxies are not just curiosities, but actual evidence that our understanding of gravity itself is flawed. Modified Newtonian dynamics, or MUND, is an alternative theory that proposes tweaking the laws of gravity to explain galactic rotation curves without the need for dark matter. However, MUND has historically struggled to explain the dynamics of galaxies within clusters. The behavior of ultra-diffuse galaxies, especially those in clusters like Dragonfly 44, presents a new and critical test. Do their stars move in ways that can be explained by modified gravity alone, or do they absolutely require the presence of a massive, unseen dark matter halo? The answer could either bolster the case for dark matter or provide the most compelling evidence yet for a gravitational revolution. By studying these faint echoes of galactic evolution, we are essentially conducting a controlled experiment on a cosmic scale. They represent a unique test case where the influence of dark matter is almost completely divorced from the complicating glare of numerous stars. They ask us a fundamental question: is a galaxy defined by its stars or by its gravity? The answer will likely reshape our models of cosmic structure and force us to acknowledge that for every grand spiral galaxy shining brightly, there could be a dark, silent twin floating in the void, holding onto its secrets in the dark. Now let's shift our focus from the grand scale of ghostly galaxies to something seemingly mundane: the faint, ubiquitous dust that drifts between the stars. For centuries, astronomers viewed this interstellar dust as little more than a nuisance, a cosmic fog that dims and reddens the light from distant objects, obscuring our view of the universe beyond. But in the last few decades, we've come to realize that this dust is far from inert. It's a dynamic and complex component of the galactic ecosystem, and it holds clues to some of the most fundamental processes in space. One of the most intriguing of these clues emerged not in visible light, but in the microwave part of the spectrum, where certain dust clouds were found to be glowing with a faint, anomalous radiation that none of our existing theories could fully explain. This mysterious signal, first detected in the 1990s by radio telescopes conducting all-sky surveys, quickly became a puzzle. When astronomers observe a cosmic cloud, they expect its microwave emission to come from two primary sources: thermal radiation, which is simply the heat emitted by warm dust grains, and synchrotron radiation, which is produced by electrons spiraling at near light speed around magnetic fields. But in many regions, particularly in our own galaxy, there was an excess of microwave light that didn't match the profile of either mechanism. It was too bright and had a spectrum that was too flat to be thermal radiation, and its polarization properties were all wrong for synchrotron. It was as if the dust itself was generating a completely new kind of light, a whisper from the microscopic world that we had never learned to hear. The hunt for the source of this anomalous microwave emission led scientists deep into the realm of nanoscale physics. One of the leading theories proposed that the culprit was something astonishingly small: tiny, spinning nanoparticles of carbonaceous dust, often likened to miniature diamonds or flakes of graphite, smaller than 1,000th of the width of a human hair. The idea is that these specks of dust, when struck by a single ultraviolet photon from a nearby star, can be set spinning at incredible rates, billions of rotations per second. This rapid rotation would cause them to emit radiation at microwave frequencies, a process known as electric dipole emission. It's a bit like a microscopic radio transmitter, with each tiny grain broadcasting its presence as it spins. This elegant explanation gained traction because it could naturally account for the specific spectrum of the anomalous emission observed across multiple wavelengths. However, not all the evidence fit this spinning dust model perfectly. In some environments, the anomalous emission seemed correlated with regions of strong magnetic fields, suggesting an alternative origin. ferromagnetic or magnetic dust grains. In this scenario, the microwave radiation isn't produced by spinning dust, but by the wobbling or precession of magnetic nanoparticles like tiny compass needles rapidly jostling and aligning themselves with the magnetic fields of the galaxy. This magnetic dust model can explain some of the polarization features that the spinning dust model struggles with, creating a fascinating scientific debate where both ideas have compelling evidence, yet neither can claim a complete victory. The truth might even be a complex mixture of both mechanisms, operating in different environments or on different types of dust grains. Unraveling this mystery is far more than an academic exercise in cataloging obscure radiation mechanisms. It strikes at the very heart of how we understand the life cycle of matter in our galaxy. Interstellar dust is not just passive scenery, it's the raw material for planet formation. It shields molecular clouds, allowing them to cool and collapse to form new stars and planetary systems. Its composition influences the chemistry of space, serving as a substrate upon which complex molecules, including the prebiotic building blocks of life, can form. If we misunderstand the fundamental nature of this dust, how it absorbs, emits, and interacts with light, then we introduce errors into every measurement that involves it. Our estimates of the mass of distant galaxies, the rates of star formation, and even the precise maps of the cosmic microwave background radiation itself are all filtered through our models of interstellar dust. An unresolved anomaly in its emission means there is a hidden variable in all of these cosmological calculations. This clue, buried for years in the background data of radio surveys, is a powerful testament to the fact that the universe is rich with complexity at every scale. The grandest galactic structures and the smallest specks of dust are intimately connected, and a faint, unexplained glow in the microwave sky can ultimately force us to reconsider our understanding of everything from magnetism on the nanoscale to the evolution of entire galaxies. It reminds us that sometimes the most profound discoveries are not made by looking past the cosmic fog, but by finally learning to see the light within it. High-energy astronomy often feels like a field of chaos, a realm dominated by random, violent outbursts, but sometimes, hidden within the apparent pandemonium, there is a subtle, rhythmic pulse, a cosmic heartbeat emanating from the most powerful engines in the universe. This brings us to the enigmatic behavior of blazars, the incredibly bright cores of distant galaxies where a supermassive black hole is actively feeding and firing a jet of radiation and particles directly toward Earth. While their emissions are famously variable, flickering unpredictably across timescales from minutes to years, a few of these objects have been caught doing something extraordinary. They're ticking. They exhibit quasi-periodic oscillations, faint but discernible rhythms in their gamma-ray and radio light that repeat over periods ranging from a few hours to several years. For a long time, these periodic signals were often dismissed as statistical flukes or mere noise in the data, the kind of random pattern the human brain is wired to find even when none exists. But what if we've been filtering out the most important signal of all, a rhythmic echo that reveals the intricate dance happening at the heart of the chaos? The most tantalizing explanation for these cosmic metronomes is the presence of a binary supermassive black hole system. Imagine two gravitational monsters, each weighing millions or even billions of times the mass of our Sun, locked in a slow, orbital waltz around a common center of gravity. As they orbit, their gravitational influence would periodically tug on the accretion disk, the swirling disk of superheated gas and dust that feeds the primary black hole. This gravitational nudging could modulate the rate at which material falls onto the black hole, creating a regular pulse in the energy output. Alternatively, the jet itself, that narrow beam of relativistic particles, could be precessing. Much like a wobbling top, the jet's axis could slowly trace a circle in the sky over many years, caused by the gravitational torque from the second black hole. As the jet swings around, its most intense radiation would sweep across our line of sight at regular intervals, producing a periodic flash in our telescopes. The discovery of such a system would be monumental, providing direct evidence for a key prediction of galaxy evolution theory, that galaxies grow through mergers and their central black holes eventually sink to the center and pair up. Yet the binary model is not the only player on the field. These rhythms could also be born from processes within the accretion disk itself. These disks are not smooth, placid rivers of gas. They are turbulent, magnetized plasmas subject to powerful instabilities. Certain types of instabilities can create standing waves or rhythmic patterns in the disk, like waves sloshing in a bowl. A specific region of the disk could periodically become overloaded with material, and then dump it all at once onto the black hole in a regular burst of accretion. Another possibility involves the physics of the jet's formation. The jet is launched and collimated by intense magnetic fields twisted up by the rotation of the black hole and the disk. If these magnetic fields become overly twisted, they can kink and then abruptly release their energy in a kind of magnetic reconnection event. If this process happens rhythmically, it could inject pulses of energetic particles into the jet at regular intervals, creating the observed periodicity from within the jet itself. Unlocking this mystery requires a new way of listening to the cosmos. It demands that we go back through decades of archival data from telescopes like the Fermi Gamma Ray Space Telescope and countless radio observatories, not to smooth out the variations, but to scour them for hidden patterns. This is a perfect task for the powerful algorithms of machine learning, which can be trained to find subtle, repeating signals buried deep within the noisy light curves of these active galaxies. By applying advanced time series analysis, the same kind of mathematics used to predict economic cycles or identify rhythmic patterns in heartbeats, we can search for these cosmic rhythms across the entire electromagnetic spectrum. A periodic signal that appears simultaneously in both gamma rays and radio waves would be a particularly strong clue, pointing to a fundamental process orchestrating the entire system. The implications of successfully decoding these signals are profound. Confirming a binary supermassive black hole system would give us a natural laboratory for studying general relativity in its most extreme regime. We could potentially measure the masses and orbital parameters of the pair, putting them on a collision course. These systems are the prime targets for future gravitational wave observatories like LISA, which will be able to hear the ripples in spacetime they produce as they spiral inward. Furthermore, understanding the intrinsic rhythms of accretion and jet formation would provide the master key to understanding how black holes convert gravitational energy into radiant energy with such staggering efficiency. These periodic echoes are more than just a curiosity. They are a direct line to the dynamics of the central engine, offering a chance to understand the precise mechanics that power the most persistently luminous objects in the entire universe. But if we are to take this cold spot seriously, we must venture into far more speculative and breathtaking territory. What if this anomaly is not a void at all, but something even more extraordinary, a bruise? This is the core of the supervoid hypothesis's most radical competitor. The idea that the cold spot is nothing less than an imprint, a cosmic scar left by a collision between our universe and another bubble universe in the vast multiverse. According to the theory of eternal inflation, our universe is just one expanding bubble in a frothing, infinite meta-universe where new bubbles are constantly nucleating and growing. Occasionally, these bubbles might collide. If a neighboring universe bumped into ours during the early stages of inflation, the energy released at the boundary of that collision would have left a distinct signature on the CMB, a circular patch that is slightly colder than its surroundings. The cold spot's size, shape, and temperature profile make it a surprisingly good match for such a cosmic crash site. This isn't just a clue about our universe, it's a potential window into the multiverse itself, a tangible piece of evidence for realities beyond our own. Of course, such a profound claim requires profound evidence, and the scientific community remains rightly skeptical. The statistical case for the cold spot's extremity has been debated fiercely. Some sophisticated analyzers argue that when you account for the fact that we've scanned the entire CMB sky looking for any anomaly, the probability of finding one this unusual isn't quite as low as it first appears. It could still be a rare fluke in a dataset brimming with subtle correlations. Others have proposed alternative exotic explanations that don't require other universes, such as the idea of a cosmic texture. In particle physics, textures are a type of topological defect, a kind of knot in the fabric of spacetime that could have formed during a phase transition in the early universe. The unraveling of such a knot would release a tremendous amount of energy, potentially creating a cold spot-like feature. While this is also highly speculative, it keeps the explanation within the confines of a single universe, a possibility that many find more palatable. The path to resolving this mystery doesn't lie in theoretical debates alone, but in new, targeted observations. If the cold spot is caused by a supervoid, then we should be able to find it by meticulously counting the galaxies in that direction. Deep galaxy redshift surveys, which map the three-dimensional distribution of millions of galaxies, are the perfect tool for this hunt. Some studies have indeed found evidence of a large underdensity in that region, but its size and emptiness don't seem quite sufficient to explain the entire CMB temperature dip. This discrepancy keeps the more exotic options firmly on the table. The next step is to look for the specific secondary effects each theory predicts. A collision with another universe would have created not just a temperature anomaly, but also a distinctive pattern of polarization in the CMB light around the cold spot. Future CMB experiments like the Simons Observatory and CMB S4 will have the sensitivity to hunt for this unique fingerprint, potentially confirming or ruling out the multiverse hypothesis with hard data. What makes the cold spot such a captivating clue is its sheer audacity. It is a small, subtle feature on a map of the oldest light in existence, yet it points toward possibilities that redefine the nature of reality. It challenges us to question whether our universe is a lone island or one of countless continents in a greater cosmic archipelago. By refusing to dismiss it as mere noise and instead pursuing its origin with relentless curiosity, we honor the very spirit of exploration. This cold patch on the sky is a reminder that the universe's greatest secrets are often hidden not in the loud, obvious signals, but in the quiet, persistent whispers that defy easy explanation, waiting for us to develop the wisdom and the tools to finally understand what they are trying to say. But if we shift our gaze from the cold, quiet echoes of the early universe to the furious, spinning corpses of dead stars, we find another kind of whisper, one written in the precise, rhythmic ticks of a cosmic clock that is ever so slowly losing time. Neutron stars are the universe's ultimate laboratories, compressing more mass than our Sun into a sphere the size of a city, creating densities and pressures so extreme that matter itself is broken down into exotic forms we can scarcely replicate on Earth. Many of these stellar remnants are pulsars, lighthouses of the cosmos that sweep beams of radiation across space with a regularity that rivals atomic clocks. As they spin, they gradually slow down, their rotation rate decaying in a predictable way measured by a value called the breaking index. According to our standard models, this index should be a simple number, 3, if the energy loss is purely from magnetic dipole radiation. But the universe, it seems, delights in complexity. For many pulsars, the measured breaking index is not 3. It's not even close. This anomaly is a subtle but persistent clue that our understanding of these incredible objects is incomplete, and that their rotational slowdown is telling a far richer story than we first assumed. The conventional explanations for these timing irregularities are dramatic in their own right. Pulsars are known to experience glitches, sudden, tiny speed ups in their rotation. The leading theory points to the interior of the star, which is thought to be a complex layered structure. The outer crust is a rigid lattice of atomic nuclei, while the inner core is a superfluid, a frictionless quantum liquid where vortices of neutrons can become pinned to the crust. As the crust slows down due to its external braking, the superfluid core, unaffected by this drag, can spin faster. Occasionally, these pinned vortices can suddenly unpin and transfer their angular momentum to the crust in a catastrophic event, causing the observed glitch, a stellar quake that momentarily makes the pulsar spin faster. It's a compelling picture, but it doesn't fully account for the long-term, systematic deviations in the breaking index. The anomalies suggest that something else is at work, a continuous process subtly influencing the spin down that goes beyond these sudden, interior rearrangements. One of the most intriguing possibilities is that we are witnessing the dynamic evolution of the pulsar's immensely powerful magnetic field. These fields are trillions of times stronger than Earth's, and they are not necessarily frozen in time. They could be slowly decaying or perhaps undergoing a process called Hall drift, where the field itself rearranges within the superconducting interior of the star. As the field changes shape and strength, so too does its ability to act as a brake on the pulsar's rotation. A decaying field would cause the spin-down rate to change over time in a way that standard models don't predict, perfectly accounting for an anomalous breaking index. This turns the pulsar's timing from a simple clock into a direct monitor of the magnetic heart of the star, allowing us to observe physics in regimes that are otherwise completely inaccessible. But the influence might not even be coming from within the star itself. Another extraordinary explanation points to an external force, a background sea of low-frequency gravitational waves. According to Einstein's theory, the motion of massive objects creates ripples in the fabric of spacetime. The universe should be filled with a stochastic gravitational wave background, a cacophony of waves from countless merging supermassive black holes throughout cosmic history. As these ripples pass through our galaxy, they would ever so slightly compress and expand spacetime itself. A pulsar's incredibly regular spin would be minutely affected by this stretching, a subtle, additional braking force imposed by the warping of the cosmos around it. Detecting this effect through precise pulsar timing is the entire goal of projects like the International Pulsar Timing Array, which seeks to use these natural cosmic clocks as a galaxy-sized detector to hear the hum of the universe's largest black holes. An anomalous breaking index could therefore be the first faint hint that this background is already leaving its imprint, a whisper of gravitational waves etched into the spin of a dead star. Despite the profound implications, these subtle rotational anomalies are often overlooked in favor of more immediately dramatic pulsar phenomena. Yet, their patient study requires a different kind of astronomy, one built on decades of meticulous, continuous observation. By building long baseline timelines of a pulsar's rotation, astronomers can disentangle the sudden glitches from the slow, secular changes in the breaking index. This long-term monitoring is what transforms a curious discrepancy into a decisive clue. Each pulsar becomes a unique experiment with its own magnetic field strength, age, and environment, offering a different perspective on the physics at play. The combined data from many such stars will eventually allow us to create a unified model that incorporates interior superfluid dynamics, magnetic field evolution, and even external influences from the fabric of spacetime itself. In the gradual, almost imperceptible slowing of a neutron star's spin, we find a deep and enduring echo, a message about the most extreme states of matter and the fundamental forces that govern the cosmos. These ancient rocks that fall from the sky are far more than simple souvenirs from the asteroid belt. They are time capsules preserving the raw materials from which our solar system was built. But when scientists began to analyze their composition with incredible precision, they found a series of tiny yet profound inconsistencies. Certain meteorites contain pockets of material with isotopic signatures that are completely alien to everything else in our solar system. For example, some show a surprising excess of neon-21, an isotope that is relatively rare in the solar wind and planetary atmospheres. Others contain xenon isotopes in ratios that defy the standard patterns we see on Earth, Mars, or the Moon. For a long time, these anomalies were brushed aside, often attributed to contamination from Earth's atmosphere or written off as measurement errors. But as our instruments improved, the signals only grew stronger and more perplexing. These weren't mistakes, they were messages. They are chemical echoes, faint whispers of elements that were forged not in the general cloud that birthed our sun, but in other, far more distant and dramatic cosmic events that occurred long before our solar system even existed. The most compelling explanation is that we are holding pieces of other stars. Within these meteorites, scientists have identified what are called presolar grains, microscopic diamonds, silicon carbide, and graphite particles that literally predate the sun. These tiny specks, just micrometers wide, condensed in the outflowing atmospheres of dying stars like red giants, or in the violent ejecta of supernova explosions. They were then cast adrift into the interstellar medium, where they drifted for millions, perhaps billions, of years before eventually being incorporated into the primordial nebula that collapsed to form our solar system. Their exotic isotopic signatures are a direct fingerprint of their stellar origin. The specific ratios of elements like carbon, nitrogen, and silicon tell us which type of star they came from. A grain rich in certain isotopes of silicon and nitrogen might have formed around an asymptotic giant branch star, while one with excess calcium-44 almost certainly owes its existence to a supernova. These grains are the ultimate cosmic immigrants, and they carry with them the unaltered chemistry of their home stars, preserved in the deep freeze of space for eons. Beyond these isolated stardust grains, some isotopic anomalies seem to paint a picture of a more localized, cataclysmic event. The early solar nebula might have been seeded by a nearby supernova, a massive star that exploded in relative proximity to our infant system. The shockwave from this explosion could have even triggered the collapse of the cloud that became our sun, while simultaneously injecting it with a specific cocktail of freshly synthesized radioactive isotopes. We see evidence for this in the form of decay products of now extinct radionuclides. For instance, the abundance of magnesium-26 in some meteorites is higher than it should be, and it correlates perfectly with the amount of aluminum present. This is considered the smoking gun for the former presence of aluminum-26, a radioactive isotope with a short half-life. Its presence means it must have been injected into the solar nebula right as it was forming, and then incorporated into rocks before it could completely decay. A nearby supernova is the perfect delivery mechanism for such a short-lived isotope, literally gifting the early solar system with a radioactive heat source that would have warmed planetesimals and driven their geological evolution. This clue transforms our understanding of the solar system's birth from an isolated event into a story deeply connected to the dynamic environment of our galactic neighborhood. Our sun wasn't born in a void, it was born in a stellar nursery, likely alongside hundreds of other sibling stars. Some of those siblings were massive and short-lived, destined to explode within a few million years. The isotopic anomalies in meteorites suggest that one of these siblings did exactly that, and its death throes profoundly influenced the life of our solar system. It provided the materials that would later heat planetary building blocks. It might have provided the trigger for the sun's formation, and it certainly left its unique chemical signature sprinkled throughout the asteroids that would eventually deliver these secrets to Earth. Unlocking the full story requires incredibly delicate forensic science. Researchers use advanced secondary ion mass spectrometry, a technique that allows them to blast tiny areas of a meteorite sample with an ion beam and measure the isotopic composition of the vaporized material grain by grain. This is how they can find and analyze individual presolar grains amidst a sea of normal solar system material. Each new measurement adds another piece to the puzzle, helping us to not only identify the types of stars that contributed to our solar system's makeup, but also to understand the timing and the mechanisms of that delivery. By reading these isotopic clues, we are effectively rewriting the history of our own cosmic origins, discovering that we are all, quite literally, made from the ashes of long-dead stars that lived and died in our corner of the Milky Way. What becomes undeniably clear from this journey through 25 cosmic whispers is that the universe's grandest truths are rarely announced with a shout. Instead, they linger in the background, in the faint signals we dismissed as static, the tiny data points we subtracted as error, and the anomalies we explained away because they didn't fit our existing maps of reality. From the fleeting, patterned burst of the WOW signal to the persistent, unmodeled drift of the Pioneer probes, each clue represents a moment where our curiosity was piqued by something that refused to conform. They are not mere footnotes in the story of science, they are the very plot twists that propel the narrative forward, challenging the chapters we thought were already written. This pattern reveals a profound and humbling lesson about the scientific process itself. Our models of the cosmos are brilliant, elegant constructions, but they are inherently simplifications. They are like a musician learning a complex symphony by first mastering the major themes, while the subtle harmonies and counter-melodies are set aside for later. The cosmic microwave background gave us the theme of the Big Bang, but the axis of evil whispers of a possible prelude. Dark matter and dark energy outline the symphony's structure, but the Hubble tension suggests a dissonance in the rhythm that we have yet to resolve. We built our understanding on what was loudest and clearest, and in doing so, we risked becoming deaf to the softer, more intricate parts of the composition. These forgotten clues are the universe's way of asking us to listen again, more closely, to the entire piece. Ultimately, this synthesis points toward a cosmos that is far richer, more dynamic, and more wonderfully strange than our textbooks could possibly contain. It suggests that reality is not a single, static painting but a layered masterpiece, with each new layer of technological capability allowing us to see more of the brushstrokes and colors that were always there, just beyond our perception. The discovery of the warm-hot intergalactic medium didn't invent missing baryons. It simply revealed where they had been hiding all along. The peculiar light curves of certain supernova didn't create new physics. They unveiled a diversity of stellar deaths we hadn't previously thought to look for. The universe is not changing, our ability to perceive its true depth is. This shift in perspective transforms every anomaly from a problem to be solved into an opportunity to be embraced. It urges us to adopt a new kind of scientific humility, one that is comfortable with not yet knowing and is thrilled by the prospect of discovery. It calls for us to become cosmic archivists, to return to old datasets with new algorithms and fresh eyes, understanding that the key to a future breakthrough might be buried in the noise of a decades-old magnetic tape. It also demands a renewed commitment to building ever more sensitive instruments, telescopes that can capture fainter light, detectors that can measure smaller forces, and satellites that can journey to new places, because each expansion of our senses unveils a new layer of the cosmic echo. Most importantly, connecting these clues weaves a new story about our place in the universe. It is a story that doesn't end with a neat and tidy conclusion, but opens onto a horizon of endless possibility. It tells us that we are participants in an ongoing, epic discovery, where the questions are as exciting as the answers. The next great revelation might not come from staring at the brightest object in the sky, but from pondering the faint, unexplained glimmer in the corner of an image, or from questioning why a spacecraft's path deviated by a mere millimeter per second. By learning to value these quiet whispers, we don't just solve puzzles, we learn to speak a deeper language of the cosmos, one that allows us to finally hear the full, breathtaking symphony of existence. We began this journey with a symphony, a universe playing a grand, eternal melody where every star and galaxy contributes its unique note. But as we've traveled through these 25 forgotten clues, we've discovered that the most breathtaking harmonies often come not from the loudest instruments, but from the faintest whispers buried deep within the cosmic static. Each anomaly, from the puzzling trajectory of the Pioneer probes to the enigmatic acceleration of Oumuamua, and from the persistent tension in Hubble's measurements to the ghostly glow of galactic radio loops, serves as a powerful reminder that the universe is far more nuanced, mysterious, and wondrous than our models could ever capture. These aren't mere errors in the data, they are invitations to look closer, to think deeper, and to remember that true discovery begins not with certainty, but with curiosity. What ties these clues together is a theme of profound humility. Time and again, we've seen how the scientific process, for all its brilliance and rigor, can sometimes overlook the most tantalizing hints simply because they don't fit within the established narrative. We subtracted the gamma-ray excess as background noise, dismissed the wow signal as a one-off anomaly, and attributed the Flyby anomaly to known physics, only to realize later that we might have been filtering out the very signals that could lead to our next breakthrough. This isn't a failure of science, it's its greatest strength, the ability to return to old questions with new perspectives, to question our own assumptions, and to embrace the unknown is what propels us forward. It's a testament to the idea that every generation of researchers stands on the shoulders of giants, yet also peers over their shoulders to see what they might have missed. Carl Sagan's words resonate now more than ever. Somewhere, something incredible is waiting to be known, and as we've seen, that something is often hidden not in distant, uncharted realms, but in the data we've already gathered, waiting for a fresh pair of eyes, a more sensitive instrument, or a bold new idea to reveal its significance. This is why we must continue to look up at the night sky with a sense of wonder and humility, to question the explanations we're given, and to remain open to the possibility that the universe still has surprises in store for us. Whether you're an avid stargazer, an amateur astronomer, or simply someone who enjoys pondering the mysteries of existence, there's a role for you in this great cosmic dialogue. Share your thoughts, your questions, and your ideas, because sometimes the next big revelation comes from a perspective no one else has considered. If this journey through the cosmos has sparked your curiosity, I invite you to join our community of explorers. Subscribe to this channel for more deep dives into the mysteries that shape our understanding of reality, from the smallest particles to the largest structures in the universe. Together, let's continue to listen for the echoes, those faint, forgotten clues that remind us the universe is still speaking, if only we're willing to hear what